Hello everyone. Welcome to the lecture series of machine learning. In this lecture, we are going to discuss about introduction to machine learning. Before understanding what is machine learning, let us see how do human beings make their decisions. For example, consider a doctor who diagnoses whether a patient is having dengue fever or not based on some symptoms like skin rash, fever, headache, cold cough, vomiting, etc. If only some of these symptoms are available for a patient, the doctor decides that the patient is not having dengue fever. But if majority of these symptoms are available for a patient, the doctor decides that the patient might have dengue fever. How does the doctor make these decisions? The doctor would have treated many patients in his past experience. So based on his experience, he analyzes the symptoms of the patients and then decides whether the patient is having fever or not. Thus, the human beings makes the decisions based on their past experiences. What are the semantics involved in this decision making? They are features and rules. Features are the symptoms and the rules are framed by the doctor based on his experience, which in turn decides the output. How do we outsource these features and rules to a machine? Here comes the role of expert systems. Based on the insights gathered from the doctor, the programmer frames the rules, which is in the form of if-then statements, and feeds it into the computer. So once the input is given to the machine decides whether the patient is having fever or not based on the rules framed. But expert systems are facing many challenges. A huge amount of data is there to process and some rules are not known, and the complexity also increases as the amount of data increases. So instead of having the human being to frame the rules, what if we can use the machine to figure out the function if we provide the needed data and the parameters for that function? So here comes the role of machine learning. Consider for example that a company is hiring some employees. It gathers the information about the candidates like 10th marks, 12th marks, graduate details, etc. and gives it to the machine. Based on this information, the machine figures out its own function and processes this information and gives the output, whether the candidate has to be hired or not. So here we have y is equal to f of x1, x2. x1 and x2 are the inputs, f is the function, y is the output. This function maps the relationship that exists between the input and the output. So thus from this we can understand that like human beings, machines can also learn from the past data with the help of machine learning algorithms. Now let us see formally about what is machine learning. Arthur Samuel first used the term machine learning in the year 1959. Machine learning is a subset of artificial intelligence, which is the most popular technique for predicting the future or classifying the information, which helps the people in making necessary decisions. Data is the core backbone of the machine learning algorithms. With the help of the historical data, we are able to create more data by training these machine learning algorithms. Machine learning combines computer science, mathematics, and statistics. Statistics is essential for drawing inferences from the data. Mathematics is useful for developing machine learning models, and computer science is used for implementing the algorithms. Why we need machine learning? Nowadays, we are witnessing a vast amount of data. In order to derive meaningful insights from these data, we need effective computational algorithms that churns the data and provides us with the useful results. Machine learning has become an essential part of modern industries like medicine, healthcare, manufacturing, banking, etc. It is utilized everywhere. The electronic devices we use, the applications that are part of our everyday life are all powered with machine learning algorithms. For example, Google is able to provide us with appropriate search results based on our browsing history. Netflix is capable of recommending the films or shows that we would want to watch based on our watch history. Now let us see how the machine learning works. We have 6 jars of machine learning, namely data, task, model, loss function, learning algorithm, and evaluation. Let us see about these jars one by one. Jar 1 is data. It is the information available in different formats like table, text, image, video, audio, etc. Information is the key to solve any problem. Where do we get this data from? If we are lucky, we can get it for free. If we are rich, we have to buy it. If we are smart, we can create our own data set. Now we have the data. What do we do with this data? So here comes the role of jar 2, that is task. So we have to identify the task to be done on the data. Consider this Facebook image where we have 3 images. So if we consider this image, we can do the face tagging. And if we consider this image, we can identify the action performed. And if we consider this image, we can identify the location. So these are the tasks identified on this particular data available. Now we have data and identify the task. Next we have to model the task. So that is the purpose of jar 3. A model is a prediction of a relation between input data and the output data. For example, consider this function y equal to f of x, where y is the output, x is the input, and f of x depicts the good relationship between them. This relationship can be anything which starts from simple linear equation y equal to mx plus c to nth degree polynomial as mentioned here. The mathematical equations that represents the probable relationship that exists between the input and output are called as models. Now we can use many equations to create a model. So how do we know which model is better? So here comes the loss function. The loss function helps us to determine the model which is closest to the true relation between the input and the output. It can be expressed as mentioned here. L is equal to summation of I equal to 1 to n yi minus f of xi whole square. So this is called as mean square error. So here L is the loss value, y is the true output, and f of x is the output curated by the proposed model. Next, we have to determine the parameters of the model. So here we can use the learning algorithm. So we can see that here we have the model f of x equal to ax1 square plus bx2 square plus cx3 square. Here x1, x2, x3 are inputs. A, B, C are the parameters which has to be identified by the learning algorithm. So our ultimate goal is to be, we have to minimize the loss function. So finally, we have to evaluate the system. That is, we have to quantify the performance of our system. So here comes the role of jar 6. Among the different models implemented, we have to find the best model. So one of the ways to evaluate the model is by prediction accuracy. Accuracy is equal to correct number of predictions divided by total number of predictions. Precision and recall makes up the accuracy. Precision relates to the number of times the model gives the right output, while recall relates to the number of times the model gives the wrong output. The evaluation is always done on the test data instead of training data. So thus we have seen about 6 jars in the machine learning. Now let us see the diagram which illustrates the concept of machine learning. So we are having the training data. Using the data, the machine learning algorithm is trained, and we have the machine learning model. After training, when we give the new input data, based on the training, the ML algorithm predicts the output. If the output is satisfactory, we have the successful model. If it is not satisfactory, again we have to train the ML algorithm. So this is the continuous process. Now let us see the applications of machine learning. We have vast number of applications, namely image recognition, automatic language translation, medical diagnosis, etc. So thus we have seen about what is machine learning and why we need machine learning in this lecture. Machine learning is basically divided into 3 main types, namely supervised learning, unsupervised learning, and reinforcement learning. Supervised learning learns from labels, unsupervised learning learns without labels, and reinforcement learning learns from experience. First, let us see about supervised learning. Here, sample labeled data are provided to the machine learning system for training, and the system then predicts the output based on the training data. In this, we have input variables x and an output variable y. and we use an algorithm to learn the mapping function from the input to the output, which is expressed as y equal to f of x. Here x is the input, y is the output, and f is the mapping function. The goal is to approximate the mapping function so well that when we have new input data x, we can predict the output variable y for that data. This diagram illustrates the concept of supervised machine learning. We have various shapes here. Each shape is provided with a label. So we have hexagon, triangle, and square. The machine learning model is trained with this labeled data. After training, whenever we provide the test data, it identifies the label for that particular data. Here we have square and triangle. This is correctly identified. So this is the concept of supervised machine learning. One example for supervised machine learning is spam filtering. So based on the training provided to the machine learning model for whether it is a spam or ham, whenever the new email comes, it categorizes it into spam or ham. The supervised classification can be further categorized into two types based on the type of the target variable. If the type of the target variable is continuous, then it is called as regression. The example for regression is house price prediction, which is based on the size, location, and other features. If the type of the target variable is categorical or discrete, then it is called as classification. The example for classification is predicting whether an email is spam or not. First, let us see basics of regression. It is a statistical approach which is used to analyze the relationship between the dependent variable and one or more independent variables. The objective is to determine the most suitable function that characterizes the connection between these variables. It finds the best fitting model which can be utilized to make predictions or draw the conclusions. It is used for predicting the continuous variables like weather forecasting, market trend analysis, etc. There are three main types of regression, namely simple regression, multiple regression, and non-linear regression. Next, let us see about classification. Here the goal is to learn a mapping from input x to output y, where y belongs to 1 to c. Here c represents the number of classes. If c is equal to 2, then it is called as binary classification. Here the output will be assumed to have either 0 or 1. If c is greater than 2, then it is called as multi-class classification. If class labels are not mutually exclusive, that is, if we describe somebody as tall and strong, then it is called as multi-label classification because we are giving two labels for one person. Next, we have imbalanced classification. It pertains to datasets where the distribution of observation in the target class is uneven. That is, one class label will have significantly higher number of observations while the other has lower count. First, let us see about binary classification. Here, the goal is to classify the input data into two mutually exclusive categories. The training data in such a situation is labeled in a binary format, for example, true and false, positive and negative, 0, 1, spam, not spam, etc., depending on the problem being tackled. Let us see an example for this. So we have image dog, which is provided to the machine learning model. It identifies whether it is a dog or not. So this is called as binary classification, which has only exactly two possible categories. Next, we have multi-class classification. Here, C is greater than 2, that is, it might have at least two mutually exclusive class labels. The goal is to predict to which class a given input example belongs to. For example, here we have four classes, that is dog, cat, horse, and mouse. All are mutually exclusive class labels. So the input image is dog. So it has to predict the exact class here. So it is predicting it as dog. So this is called as multi-class classification. So multiple classes labels will be provided. Among that, we have to choose the exact class for the input image. Next, we have multi-label classification. Here we try to predict 0 or more classes for each input example. Here there is no mutual exclusion because the input example can have more than one label. For example, we have input image here which contains both cat and dog, and we have classes dog, cat, horse, mouse. So it has to predict both dog and cat for this input image. So multiple labels has to be assigned to this particular image. So this is called as multi-label classification. Next, we have imbalanced classification. Here the number of examples is unevenly distributed in each class. That is, we can have more of one class than the others in the training data. For example, consider the 3-class classification scenario where the training data contains 60% of trucks, 25% of planes and 15% of boats. The objective is to predict whether a new data point belongs to the minority class even though there are many more examples in the majority class. For example, a medical diagnosis algorithm could be used to predict whether the patient is having a rare disease even though there are many more patients with the common diseases. So we have to exactly identify even the majority of patients is having common disease. If one new patient comes with a rare disease, we have to check whether he belongs to the minority class or not. So this type of classification is called as imbalanced classification. Now let us see about unsupervised machine learning. This is a learning method in which machine learns without any supervision. The training is provided to the machine with a set of data that has not been labeled, and the algorithm needs to act on the data without any supervision. The goal is to restructure the input data into new features or a group of objects with similar patterns. Here we don't have a predetermined result. The machine tries to find useful insights from the huge amount of data. It can be further classified into two, that is clustering and association. Now let us see about working of unsupervised learning. Here we have unlabeled input data, which means that it is not categorized and corresponding outputs are also not given. Now this unlabeled input data is fed to the machine learning model in order to train it. First it will interpret the raw data to find the hidden patterns from the data, and then will apply the suitable algorithms like k-means clustering, decision tree, etc. Once it applies the suitable algorithm, the algorithm divides the data objects into groups according to the similarities and differences that is available between the objects. So this diagram illustrates the working of unsupervised learning. So here we have unlabeled data, that is raw data, which contains the images of dog and cats. So the machine learning model is trained with the raw data. After training, it categorizes the images into two groups, that is dogs and cats, based on the similarities and differences. So this is the concept of unsupervised learning. Next, let us see about types of unsupervised machine learning algorithms. So first one is clustering. It is a method of grouping the objects into clusters such that the objects with most similarities will be in the one group and the less or no similarities with the objects of another group. This finds the commonalities between the data objects and categorizes them as per the presence and absence of those commonalities. Next, we have association. It is an unsupervised learning method which is used for finding the relationship between the variables in the large database. It determines the set of items that occurs together in the data set. It makes the marketing strategy more effective. Like people who buy X are also tend to purchase Y. For example, people who try to buy bread are also tend to buy the butter or jam. So best example for this association rule is market basket analysis. Next we have reinforcement learning. This agent learns by interacting with its environment. The agent will receive the rewards by performing correctly, and if it is performing wrongly, it will get the penalties. It learns without any intervention from the human by maximizing its reward and minimizing its penalty. It is a type of dynamic programming that trains the algorithms using a system of reward and punishment. So this diagram illustrates the concept of reinforcement learning. So we have the agent here and we have the environment with fire and water. So first the agent observes the environment and selects the action using its policy. So first it selects the fire. So once it is going to the fire, it gets the punishment because it is the wrong option. So minus 50 points is given as punishment. So based on this punishment, it will update its policy. And based on the learning step, it won't repeat it further. So this iterates until an optimal policy is found. So this is the concept of reinforcement machine learning. So thus in this lecture we have seen about types of machine learning. Consider that we have a training set comprising n observations of x, which is written as x1 to xn transpose, together with corresponding observations of the values of t, which is denoted as t1 to tn transpose. Here transpose is used to represent x and t as column vectors. X indicates the input features and t indicates the corresponding target values. Our goal here is to predict the value of t for some new value of x. Assume that we have the training data set of n equal to 10 points, which is represented as blue circles as shown in this diagram. The green curve here shows the actual sine function which is used to generate the data. Our objective here is to predict the value of t for some new value of x without the knowledge of this green curve. We can try to fit the data by using the polynomial function of the form y of x comma w, which is represented as w0 plus w1x plus w2x square up to wm into x bar m. In short, we can represent this as summation of wj into x bar j, where j is equal to 0 to m. Here w0 is a constant and w1 to wm are the coefficients or weights which is used to scale the input features. The values of the coefficients will be determined by fitting the polynomial to the training data. This can be done by minimizing an error function that measures the misfit between the y of x comma w and target t. So as shown in this diagram, y of xn comma w is the predicted value and tn is the target value. So we have to minimize the error between these two values. So this can be done by using the error function, which is nothing but the sum of squared error between the predicted value and the target value. So we have to choose the value of w such that E of w is as small as possible. The resulting polynomial is given by the function y of x comma w star. Choosing the order m of the polynomial is called as model selection. In this diagram, we can see different fits for m equal to 0, m equal to 1, m equal to 3 and m equal to 9. So here green color indicates the existing sine curve and red indicates the new fit. So for m equal to 0 and m equal to 1 polynomials, we can see that we have the poor fit to the data and it is also giving the poor representation of this green curve. So this red line is not aligning to this green curve for m equal to 0 and m equal to 1. The third order m equal to 3 polynomial seems to give the best fit here because it is more or less aligning to the existing sine curve. And if we see for the m equal to 9, we obtain an excellent fit to the training data. In fact, the polynomial exactly passes through each of the data point. So here E of w star is equal to 0. We obtain an excellent fit to the training data with 9th order polynomial. However, the fitted curve oscillates widely and gives a very poor representation of the sine function, which is represented as green curve here. So this behavior is called as overfitting. We have to avoid overfitting. We can evaluate the residual value of E of w star for training data and test data using the root mean square error, which is represented as square root of 2e of w star divided by n. Here division by n allows us to compare the different size of data sets. This diagram illustrates the root mean square error for test data and training data. So here test data is represented with red line and training data is represented with blue line. We can see that the error increases as the degree of the polynomial increases for the test data and it decreases for training data. So this indicates that for higher degree polynomial, the data overfits for training data and it is not giving the good representation for test data. So from this we can understand that we should choose the moderate degree of polynomial so that we can get best fit for both training data as well as test data. The magnitude of the coefficients will increase dramatically as the order of the polynomial increases. Particularly between the data points, there might be large oscillations which leads to overfitting. So here for degree m equal to 9, we can see the large oscillations between the coefficients which will lead to overfitting. So we should avoid the overfitting. Now let us see an example for polynomial curve fitting. Consider that we need to fit an nth order polynomial to set of points. We can express this in the equation as f of x is equal to a0 plus a1x plus a2x square plus up to an into x power n. So here totally we have n plus 1 points, that is from a1 to an. In addition to that we have a0. So these n plus 1 points can be represented in the matrix as shown here. So f of x is represented as f of x1 to f of xn plus 1. And since we don't have any input feature associated with a0, we are using 1 here, and all the input features are represented here x1 square up to xn per n. So it is represented until xn plus 1, and we write this coefficients a0 to an as the separate vector here. So in short we can write this as f is equal to x into a. So this is f, this is x, and this is a. So to get a, we can write it as x inverse into f. So that is the inverse of x multiplied by the matrix of f. Now let us try to fit the following points in a polynomial curve. The points given are f of 0 is equal to 0, f of 1.5 is equal to 1.5, and f of 4.0 is equal to 1. The first step is we have to write the equation for this. So we can write the equation as f of x is equal to a0 plus a1x plus a2x square. So since we have 3 points, we can stop up to x square. And then the next step is to represent the equation in the matrix form. So this equation can be expanded like this. So since we have 3 points, we have f1, f2 and f3 here. f1 is a0 plus a1x1 plus a2x1 square. And f2 is equal to a0 plus a1 x2 plus a2 x2 square, and f3 is equal to a0 plus a1 x3 plus a2 x3 square. In short, we can write this as f1, f2 and f3. So for the right side of the equation, this constant is represented as 1 here since we don't have anything associated with a0. And for a1 and a2 we have x and x square. So we write it as x1, x2, x3, and then x1 square, x2 square and x3 square. This a0, a1 and a2 are represented here. Now let us substitute the values given here for the matrix. So for f1, f2, f3 we have the values 0, 1.5 and 1. So that is substituted here. And for x1, x2, x3, so we have for constant we make 1 as it is. For x1 it is 0, and for x2 it is 1.5, and for x3 it is 4. Next for x1 square, x2 square and x3 square we square this column. So we get 0 for x1 square, and for x2 square it is 2.25, and for x3 square it is 16. Now we have to find the value of a. So what we have to do means we have to take the inverse of x and multiply it with f. So we are doing that here. So once we multiply this, we get the value for a0, a1 and a2 as 0, 1.45 and minus 0.3. Since a0 is having 0 here, we are omitting it and we are writing the equation as 1.45x minus 0.3x square. So this is our final polynomial which is represented in this curve. So here in the origin we have 0, it represents a0, and then this represents the a1 and this represents the a2. So thus we have seen the example for the polynomial curve fitting. Probability indicates how likely something is to happen. It analyzes the chances of events occurring. The values of the probability ranges from 0 to 1. 0 indicates that the event cannot happen, while 1 indicates that the event is guaranteed to happen. The middle value 0.5 signifies that the event is equally likely to happen or not. For example, in a coin flip, the probability of occurrence of heads will be equal to the likelihood of not occurrence of tails. Basically, the probability of an event occurring can be expressed using this formula. That is the number of ways the event occurs divided by total number of outcomes. For example, if we consider a coin toss, the probability of getting a head is equal to 1 by 2. Here, numerator represents the number of ways the event occurs. So in a coin toss, there is one possibility for getting a head, and denominator indicates the total number of outcomes. So here we have only two possible outcomes, that is head or tail. So thus the probability of getting a head in a coin toss is equal to 0.5. Now let us see about union of two events or sum rule in probability. Consider that we have two events A and B. We can define the sum rule for these events as follows. So the sum rule can be expressed by using either the or symbol or union symbol. So we have two set of rules here. First one is for non-mutually exclusive events and second one is for mutually exclusive events. So for non-mutually exclusive events, the rule can be written as probability of occurrence of A plus probability of occurrence of B minus probability of occurrence of A and B together. For mutually exclusive events, it can be written as probability of occurrence of A plus probability of occurrence of B. Let us understand the difference between mutually exclusive events and non-mutually exclusive events. Non-mutually exclusive events means there is some dependency between the two events A and B. So we have the common part between A and B here. This is called as intersection of two events. So while writing the sum rule for non-mutually exclusive events, we have to eliminate this common part. So thus it has been written as P of A plus P of B minus P of A intersection B or P of A and B. For mutually exclusive events, there is no dependency between the two events. They occur separately. So in this case, we can write the rule as P of A plus P of B. So this is the sum rule in probability. Now let us see about joint probability or product rule. It is the likelihood that two or more events will coincide or occur together. For example, getting two heads in two coin tosses which occur at the same time. We can use the notation P of A intersection B to denote the joint probability of the events. It is also known as intersection of events. We can express the product rule either by using the and symbol or intersection. So we can write the product rule as P of A and B is equal to P of A given B into P of B. So this is called as conditional probability. The P of A given B is called as conditional probability. There are several methods to represent these joint probabilities. Three standard methods are contingency tables through independent events and dependent events. First, let us see about the contingency table or joint probability table. When we are dealing with multiple events, creating a table to organize the likelihoods can be helpful. This table lists the chances of event combinations at each row and column intersection. Let us consider an example. Suppose that Amazon Network took a survey of 500 subscribers about their favorite category of shows as mentioned in this table. We have three categories of shows, that is fantasy, action and others, and subscribers are male and female. Totally we have 500 subscribers. So the number of male watching fantasy is 80, female watching fantasy is 120. So like this we have for other shows also. So this can be expressed in terms of probability like this. So here we are dividing each cell by the total number of subscribers. So the probability of male watching fantasy show is 0.16, which is nothing but 80 divided by 500. And female watching fantasy show is 0.24, which is 120 by 500. So this probability of female watching fantasy show, that is called as, this intersection is called as joint probability. So all the text highlighted in red in these cells indicates the joint probability. If we sum up these joint probability, then it will be equal to 1. Now we have marginal probability. So the total of the shows and the total number of male subscribers and female subscribers indicates the marginal probability. So now even if we sum this marginal probability, we will be getting the sum as 1. So in this slide we have seen about joint probability and marginal probability. So we can see that the intersection of the row and column indicates the joint probability and the total indicates the marginal probability. Now let us see the joint probability through dependent events. If the outcome of the first event affects the probability of the second events, then we say that the events are dependent. Let us consider the same example. So here we say that this is dependent event because the outcome of this event is affecting this event. So the probability of female watching fantasy, there is dependency between these two events. So that's what it is called as dependent event. So if the event is dependent, then we can write the product rule as P of A intersection B is equal to P of A given B into P of B. So here we know that the P of A given B is conditional probability. And we can write this conditional probability as P of A given B is equal to P of A intersection B divided by P of B. So we are taking this P of B to the denominator of P of A intersection B. Now let us see whether we are able to get this 0.24 if we apply the values for this product rule. So we are considering A as female and even B as fantasy. So to find the conditional probability for P of female given fantasy, the formula is P of female intersection fantasy divided by P of fantasy. So female intersection fantasy, according to this table, it is 0.24 and P of fantasy is total number of fantasy shows, that is 0.4. So we get 0.6. So let us substitute this 0.6 into this product rule. So P of A intersection B means P of female intersection fantasy, that is equal to P of A given B is 0.6 here and P of B is nothing but P of fantasy, which is 0.4. So if we multiply, we are getting 0.24. So like this, we can find the joint probability using this product rule also. So the answer is similar to the answer what we are seeing in the intersection of this table. Next, we have independent events. So if the outcome of the first event does not affect the probability of the second event, then these events are said to be independent events. If the events are independent, then we can express the conditional probability P of A given B as just P of A. Because there is no dependency between A and B means we can represent it as just P of A. Similarly, for P of B given A, we can represent it as P of B. And the product rule can be written as P of A intersection B is equal to P of A into P of B. Because there is no relevance between A and B. So this independence can be expressed by using this perpendicular operator. So let us see an example for independent event. Assume that we have two events, that is throwing a dice and toss of a coin. So that is X and Y. So we can express this in terms of product rule as P of X intersection Y is equal to P of X into P of Y. P of X is throwing a dice, P of Y is toss of a coin. So throw a dice means we will be having 1 by 6 as the outcome. And for tossing a coin, it is 1 by 2. So thus we have 1 by 12. So this is an example for independent event for joint probability. Next, we'll see about conditional probability. So let us consider the same example. So conditional probability can be expressed as P of A intersection B divided by P of B. So let us see an example for this conditional probability. The question is, Sheetal just got an Amazon subscription. What is the chance that her favorite show type is fantasy? So here we are given with the concept that Sheetal is a female. So we know that the subscriber is female. So we have to find the chance that what is the chance her favorite show will be fantasy. So we can write it as P of fantasy given female. So we know that the subscriber is female. So what is the probability of this female watching the fantasy show? So it can be written as P of A intersection B divided by P of B. P of A intersection B means fantasy intersection female. So that is nothing but 0.24 divided by P of female. P of female means total number of female subscribers, that is 0.54. So we are getting 0.44. So this is the conditional probability. So thus we have seen some basic concepts of probability in this lecture. Before understanding about random variables, let us see about random experiment and sample space. A random experiment is a type of experiment that has multiple possible outcomes. Such an experiment can be repeated many times. Any outcome of a random experiment cannot be predicted until the experiment has been performed. Example for random experiment is tossing a coin and throwing a dice. In these two experiments, we will not be knowing the outcome until it is being performed. And if we repeat this many times, it will yield different possible outcomes each time. Sample space is the set of all possible outcomes for a random experiment. For example, in tossing a coin, the possible outcomes will be head and tail. If we are tossing the coin twice, the possible outcomes will be head, 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 tail, tail, head and tail, tail. Now let us see about random variables. It's a function which performs the mapping of the outcomes of a random experiment to a numerical value. The random variable is denoted by capital letter X and its value is denoted by a small letter x. For example, if we flip 5 coins and want to answer the question like what is the probability of getting exactly 3 heads, then we can express it as P of x equal to 3. Here x is the random variable and 3 is the numerical value assigned to this random variable x. Types of random variables. Random variables can be either discrete or continuous. If a variable can take countable number of distinct values, then it is called as discrete random variable. For example, in an experiment of tossing 2 coins, the possible number of outcomes will be head, 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 tail, tail, head and tail, tail. So if you want to find out the possible number of heads in this coin toss, then it can take any of these 3 values, that is 0 in case of tail, tail, 1 in case of head, tail and tail, tail, 2 in case of head, head. So thus the random variable x can take 0, 1 or 2, which is discrete. A random variable is said to be continuous if it takes infinite number of values in an interval. For example, suppose the temperature in a city lies between 30 degree and 45 degrees centigrade. The temperature can take any value in the interval between 30 degree and 45 degree. So the temperature can be either 30.13 or 40.15 etc. So there is nothing exact or discrete observation in continuous random variable. Now let us see about probability distributions. It is a statistical function which links or lists all the possible outcomes a random variable can take in any random process. So if it is a discrete random variable, then the probability distribution is called as probability mass function or PMF. So we know that discrete random variable takes only finite set of values, and some examples are number of typo errors, number of diagnostic errors, etc. For continuous random variable, the probability distribution is called as PDF or probability density function. So here it holds different values from an interval of real numbers. Example is temperature, pressure, height, etc. First let us see about probability mass function or PMF. It lists possible values of different outcomes and their respective probabilities. Let us consider as an example of rolling a dice. So if x is a random variable associated with rolling of a 6-sided fair dice, then the PMF of x can be given as shown in this table. So here x can take any value from 1 to 6 and the probability of x equal to x can be represented as 1 by 6. So here 6 is the total number of outcomes in the dice. And probability of getting 1 is 1, probability of 2 is getting 1. So it is mentioned as 1 by 6 for each cell. So graphically it can be represented like this. So you can see from this graph that it is discrete. So to be a PMF of a random variable x, a function p satisfies the following conditions. Domain of p is the set of all possible states of x. So as mentioned here, the domain will be set of all possible states of x, and if we sum up all these probabilities, then it will be getting the value as 1. So that is mentioned in this third condition, and the value will be between 0 and 1. So because the maximum value itself 1 only, so it should take only the values between 0 and 1. So this is the probability mass function. Next, probability density function or PDF. So it is the probability per unit length or interval. Let us consider as an example amount of rainfall between 10 and 20 centimeter, which can be expressed as P of 10 less than or less than 20, or P of 10 less than or equal to or less than or equal to 20. So R is the rainfall, amount of rainfall ranges between 10 and 20. So we can represent this in PDF as integral. So integral of 10 to 20 f of x dx. So in general we can represent it as integral of a to b f of x dx. So here a and b are the intervals. So graphically it can be expressed like this. So this is the interval which is expressed as PDF. The PDF should satisfy the following properties. Domain of P is the set of all possible states of X, which is similar to PMF, and here the values should be non-negative, that is f of x should be greater than or equal to 0 for all x, and the area between the density curve and the horizontal x-axis will be equal to 1. That is the integral of f of x dx is equal to 1. Finally, let us see about cumulative distribution function. All random variables, discrete or continuous, will have the cumulative distribution function, which is represented as CDF. Corresponding to any distribution function, there is CDF denoted by f of x, which for any value of x star gives the probability of the event as x less than or equal to x star. So therefore, if f of x is PMF of x, then the CDF can be given as f of x star is equal to summation of f of x. So here x is less than or equal to x star and value of x lies between minus infinity to x star. Similarly, for continuous random variable, we can express it as, so it is expressed as integral. So here it is mentioned as summation since it is PMF. For PDF it is expressed as integral. So integral of minus infinity to x star f of x dx. So x takes the value between minus infinity to x star. So thus we have seen about random variables and probability distributions in this lecture. First let us see about expectation of a random variable. The expected value of a random variable, also called as mean, is denoted by E of x or mu. It is the weighted average of the possible outcomes of a random variable, where the weights are the probabilities that the outcomes will occur. It can be expressed as E of x is equal to summation of x into P of x equal to x. Let us see an example for calculation of expectation. Consider the rolling of a dice. The expected value for the rolling of a dice can be calculated as shown here. So x contains the possible values it can take for rolling of a dice. So it is from 1 to 6. The probability of getting 1 in rolling of a dice is 1 by 6. 2 is 1 by 6. Likewise up to 6 we are representing. So the idea behind this equation is we have to multiply the x with its individual probabilities. So if you multiply 1 into 1 by 6 plus 2 into 1 by 6 up to 6 into 1 by 6, we get 21 by 6, which is nothing but 3.5. Thus the expected value for rolling of a dice is 3.5. Next let us see about variance. It measures how closely the values are spread around the mean. It is denoted by VAR of x or sigma square x. It is expressed as sigma square x is equal to E of x minus mu x whole square. This is the expected value of the square difference between x and its mean. For a discrete distribution, we can write the variance as summation of x minus mu x whole square into P of x equal to x. For continuous variable, we can express the same equation as integration. So variance of x is equal to integration of x minus mu whole square into f of x dx. Standard deviation of a random variable is the square root of its variance and is denoted by sigma x. The greater the standard deviation, the more spread out the possible values of the random variable. We can write this variance formula E of x minus mu x whole square as variance of x is equal to E of x square minus E of x whole square. So let us see how we can derive this formula from this expression. So consider we have variance of x is equal to E of x minus mu whole square. We can write this expectation in the form of summation of x minus mu whole square into p of x. So expanding this formula, we can write it as x square minus 2 mu x plus mu square into p of x. So let us take summation for individual terms. So summation of x square into p of x minus 2 mu into x into p of x plus mu square into summation of p of x. So in this case, we can represent summation of x square into p of x as e of x square, because summation of x square is nothing but e of x square minus 2 mu square. So summation of x into p of x can be expressed as mu. So 2 mu into mu can be written as 2 mu square. So it is plus mu square. So we get, after subtracting this, we will get mu square. So it is e of x square minus mu square. So mu square we can write it as e of x whole square. So thus we arrive at e of x square minus e of x whole square. So the variance can also be expressed as e of x square minus e of x whole square. So let us see an example for variance and standard deviation. So consider rolling of one dice. So the solution is, we can write the variance of x as e of x square minus e of x whole square. We know that e of x is 3.5 to roll a dice from our previous explanation. So now we can calculate e of x square as x square into p of x. So it will take values from 1 to 6. So possible values of x has to be squared. So 1 square into 1 by 6 plus 2 square into 1 by 6 up to 6 square into 1 by 6. It is 15.167. So we subtract this from e of x whole square. So e of x whole square is 3.5 whole square. So we get 2.917. So if we take square root, we get 1.708, which is nothing but the standard deviation. So thus we have found the variance and standard deviation for rolling one dice. Next, covariance. The covariance of random variables x and y, which represents the relationship between these variables, is denoted as e of x minus mu x into y minus mu y. It tells us the direction in which two quantities vary with each other. This can be simplified as shown here. So let us take the formula x minus mu x into y minus mu y. So we can multiply these terms and write xy minus mu yx minus mu xy plus mu x mu y. So applying expectation for individual terms, we can write it as e of xy minus mu y into e of x minus mu x into e of y plus mu x into mu y. So we can write this e of x as mu x, e of y as mu y, and this cancels, minus mu x mu y and plus mu x mu y gets cancelled. So final formula is e of xy minus mu x mu y. So thus the covariance can be simplified as e of xy minus mu x into mu y. So let us see an example for covariance. Suppose that x and y have the following joint probability mass function. Let us calculate the covariance in terms of x and y. So the formula is e of xy minus mu x into mu y. So in this, we rewrite the formula as summation of xy into f of xy minus mu x mu y to solve this problem. So xy is nothing but the row is x and column is y. So 1 into 1. So you have 1 for x here. So 1 into 1, that is x into y. 1 into 1 into f of x comma y. F of x comma y is this joint probability distribution. So 1 into 0.25, which is expressed as 1 by 4, plus 1 into 2 into 1 by 4, plus 1 into 3 into 0 as mentioned here, plus next we come to the second row, 2 into 1 into 0, 2 into 2 into 0.25 is 1 by 4, 2 into 3 into 1 by 4 again, minus mu x mu y. So mu x is this sum divided by its total number. So 2 plus 1 3 divided by 2. So minus 3 by 2 into mu y. So this one 3 plus 2 plus 1, it is 6 divided by 3, it is nothing but 2. So minus 3 by 2 into 2 can be expressed as 3. So if we calculate this, we final value is 1 by 4. So thus the covariance of x and y is 1 by 4. Finally, let us see about quantiles. Quantiles are values that split sorted data or the probability distribution into equal parts. The median is a quantile. The median is placed in a probability distribution so that exactly half of the data is lower than the median and half of the data is above the median. The median cuts a distribution into two equal areas, and so it is sometimes called as two quantile. In general, a Q quantile divides sorted data into Q parts. The most commonly used quantiles have special names as mentioned here. So it is quartiles, that is 4 quantiles, splits data into 4 parts. Deciles 10 quantiles, splits the data into 10 parts. Percentiles is 100 quantiles, splits the data into 100 parts. So generally we can represent the ith observation as q into n plus 1, where q is the quantile, which is nothing but the proportion below the ith value that we are looking for, and n is the number of items in the data set. Let us see how to find quantiles using an example. So we have some data here. We have to find the number in the following set of data where 20% of values fall below it and 80% fall above it. So the steps are, first one is we have to sort the data from smallest to largest. So the data is already sorted, so we'll go for step 2. We have to count the number of observations. So total number of observations is 40 in this data. Step 3 is convert any percentage to a decimal for Q. So any percentage means here we have 20% and 80%. So let us consider 20% and convert it to decimal. So it is represented as 0.2, which is for value for Q. Next, let us insert these values into the formula. Ith observation is equal to Q into n plus 1. So Q is 0.2. So n is 40 plus 1, that is equal to 8.2. So if we round off the 8.2, we will get 8. So 8th number, if you check, it is 13. So thus it says that 20% of it total data is falling below this 8th number and remaining 80% is above it. So this is called as quantiles. So thus in this lecture we have seen about variance, covariance, standard deviation and quantiles. Assume that we are given some observed data. Maximum likelihood estimation or MLE is a method of estimating the parameters of an assumed probability distribution for the given observed data. This is achieved by maximizing the likelihood function so that under the assumed probability distribution or statistical model, the observed data is most probable. The point in the parameter space that maximizes the likelihood function is called as the maximum likelihood estimate. The goal of the maximum likelihood principle is to fit an optimal statistical distribution to some data. This makes the data easier to work with, which makes it more general, allows us to see if the new data follows the same distribution as the previous data, and also allows us to classify the unlabeled data points. Now let us imagine a binary classification problem between male and female individuals using height. Once we have calculated the probability distribution of men and women heights and we get a new point as height with no label, we can assign it to the most likely class, seeing which distribution reports the highest probability of the two. For example, consider this image. So we have blue line which is for male distribution and red line for female distribution. So now assume that we have new unlabeled data point, that is x new. So here x axis is height in centimeter, y axis is class probability. So in this image, the new data point which corresponds to a height of 172 centimeter. So 172 centimeter means here it is classified as female because for the specific height value, the female height distribution yields a higher probability. So if you see here, the female distribution yields a higher probability than the male one. So we decide that this new data point belongs to the female distribution. We know that the goal of MLE is to fit the optimal probability distribution to some data. Now let us see how to calculate the distributions or estimate the parametric density function. Let us denote our data vector of size n as x. In this vector, each of the rows is a data point with d features. Now we have our data. Once we have collected the data, we need to guess the kind of probability density function or distribution which we think our data follows. There are many types of distributions like Gaussian, exponential, Poisson, etc. We can use any of this. In our case, we are considering the Gaussian or normal distribution. Let's call the overall set of parameters for the distribution as theta. So in the case of normal distribution or Gaussian distribution, the parameters are mean and the variance. Now we need to obtain the parameter set theta that maximizes the joint density function of the data vector, that is the likelihood function, which is mentioned as L of theta. The likelihood function can also be expressed as P of x given theta, which is written as L of theta is equal to P of x given theta is equal to P of x of 1 to x of n given theta. Here x is the data matrix, x of 1 up to x of n are each of the data points in the data matrix X, and theta is the given parameter set for the distribution. The goal of the maximum likelihood principle is to choose the parameter values, that is theta, so that the observed data is as likely as possible. To obtain this optimal parameter set, let us take the derivatives with respect to theta in this likelihood function, which is expressed here. If the data points of this x is independent of each other, then the likelihood function can be expressed as the product of the individual probabilities for each data point as given here. So we can express this likelihood function as L of theta is equal to P of x given theta is equal to product of P of xj given theta. So here xj is nothing but x of 1 to x of n. Now let us see about the maximum likelihood principle using normal distribution. For normal or Gaussian distribution, the parameters are the mean and the variance. The density function for the normal distribution or Gaussian distribution can be expressed as f of x given mu comma sigma square, which is equal to 1 by root of 2 pi sigma square into e power minus of x minus mu whole square divided by 2 sigma square. Here x is the input data, mu comma sigma square are the parameters which is represented as theta, and mu is the mean, sigma square is the variance. Now let us consider the likelihood function for first data point in a data set. So the equation can be modified as P of x of 1. So here instead of x we have x of 1 and the parameters are mu comma sigma square, and the formula is same, except instead of x here we are mentioning it as x of 1 since we are considering the first data point. So this is the equation for the first data point. If we consider the n data points, that is whole data set, then the equation will be like this. So instead of x of 1 we have x here, and this root of 2 pi sigma square can be expressed as 2 pi sigma square whole power 1 by 2. So instead of square root we can express it as exponentiation of 1 by 2. So since here we are considering n data set, it is expressed as 2 pi sigma square whole power n by 2. And here instead of x of 1 we have x of I, and we have summation here since we are considering the n data points. So this is the equation for whole data set. Now let us express this probability distribution equation for whole data set in a logarithmic way as shown here. So if we apply logarithm for this first term in the equation, we get minus n by 2 into ln of 2 pi sigma square. This is because 1 by log x can be expressed as minus log x, so we have minus here. In turn, we can express log of x power n as n log x. So we have 2 pi sigma square whole power n by 2. So we can express it as n by 2 into ln of 2 pi sigma square. And if we consider this part, log of e power x can be expressed as just x. So here we have the form e power minus x. So we take this term as it is. So minus 1 by 2 pi sigma square into summation of x of j minus mu whole square. Now after taking the logarithm, we set the derivative for this likelihood function with regards to mean to 0. So first let us take the derivative for this equation as shown here. Here first term is not depending upon the mu because we don't have mu term at all here. We have only sigma square. So the derivative with respect to mu is set to 0 for this term. So we are considering only the second term. So we are applying the derivative for the second term alone. Now for expanding the sum, let us take the derivative inside the summation as mentioned here. After this, let us differentiate inside the sum. After differentiation, we get 2 into x of j minus mu into minus 1. So if we apply differentiation for x of j minus mu whole square, we can write it as 2 into x of j minus mu, and in terms of mu we can write it as minus 1. So we can further simplify this equation by cancelling 2 and 2 here, and minus also gets cancelled. So we can write the equation as 1 by sigma square into summation of x of j minus mu. So let us set this derivative to 0 as shown here. After setting it to 0, let us multiply both sides by sigma square. So if we multiply both sides by sigma square, this becomes 1 and this becomes 0. So we have summation of x of j minus mu is equal to 0. So let us distribute the summation for both of these terms. So we can write it as summation of x of j minus summation of mu is equal to 0. Since mu is constant with respect to j, we can simplify further as summation of x of j minus n mu is equal to 0. Now we have to find the mu, so we can write the equation as mu is equal to mu ml is equal to 1 by n into summation of x of j. So here ml indicates maximum likelihood. Now we have estimated the mean. We can do the same for other relevant parameter, that is variance. But once we have the mean, it is easy to calculate the variance, because variance is nothing but the sum of square difference between the observed data and the mean. So we can write the variance equation as variance for maximum likelihood is equal to 1 by n into summation of x of j minus mu ml whole square. So this is the equation for variance. Now we know the estimates for the parameters mean and variance of the Gaussian distribution using maximum likelihood. Let us apply this concept with an example. So we have a data set of male heights in a certain area, and we want to find an optimal distribution to it using maximum likelihood. So imagine our data vector x in our case is the following. So we have 10 data points here. So the mean for this data points is 174.5, which we get by applying these data set in the formula given here. And let us find the variance by using this equation. So we have 30.45 for variance, and standard deviation is nothing but the square root of the variance, which is nothing but 5.5 centimeter. Now for any new data 177, let us check whether it is fitting to the following distribution or not. So we have 177 here. So let us substitute this 177 in this equation of Gaussian distribution. So for x we have 177, that is new data, and mu and sigma square. Mu is the mean. For mean we have 174.5 and variance we have 30.45. So if we calculate by substituting these values in the equation, we get 0.0652 as the distribution value. Here is the normal distribution curve for the given data set of male heights with a mean of 174.5 cm and variance of 30.45. So this blue line is the normal distribution curve for this particular mean and variance. Now let us see whether this new value 177 is fitting to this distribution or not. So we have 177 here, which is represented in the red line. So it fits to the distribution. So the y-axis is 0.065 as we found. So thus this new value is fitting to this distribution. So this is the concept of maximum likelihood estimation. So the goal of MLE is to check whether the new value is fitting to the existing distribution or not. So thus we have seen about maximum likelihood estimation in this lecture.
Regression is the prediction of dependent variable from the knowledge of one or more other independent variables. And this regression analysis is a statistical technique where we can estimate the parameters of an equation relating to a particular value of dependent variable to a set of independent variables. The resulting equation is what we call it as regression equation. Given the data on years of experience and the corresponding salaries for a group of employees, now we are going to check how can we model the relationship between them using linear regression also. We can compute the predicted salary for an employee if the number of years of experience is given. This is the problem statement. Here in the problem statement, this represents the years of experience and this represents the corresponding salaries given in $1,000. We are going to predict an employee's salary based on the years of experience using linear regression. The first step is we will find the linear regression equation. Once the equation is found, we can substitute the value of the years of experience, then we can predict the employee salary based on that. Now, this is the data given, years of experience and the salary. Now, we are going to do the prediction using least square method. So, if the years of experience is given, we will be able to find out the salary. And this is possible only after finding out the linear regression equation using least square method. Now let us see how to do that. Linear regression. The first equation given here is y cap equal to beta naught plus beta 1 x. Beta naught represents the intercept, beta 1 represents the slope of the line, the coefficient for years of experience. Now using the given data, let us predict the employee salary. The first step is we need to compute beta 1. Beta 1 is equal to summation of I ranging from 1 to n xi minus x bar into yi minus y bar divided by the summation of I from 1 to n xi minus x bar the whole squared. Here x bar represents the average of x values, that is the years of experience. Y bar represents the average of all the y values, that is the salary. And xi, yi represents the x and y data points. So if there are n data points, we'll have to include all the data points starting from x1, y1 to xn, yn. The first step is to compute the average of x, that is the years of experience. We are getting 9.1 as the value. Next step is we are computing the average of y bar, that is the average of salary, which is 55.4. Once x bar, y bar are found, we need to compute the numerator and the denominator separately. For each of the data points x1, y1, xi, yi, starting from x1, y1 to xn, yn, for each of the data points we calculate this product xi minus x bar into yi minus y bar. We are computing it separately for each of the data points, and xi minus x bar the whole square, that's again computed for each of the data point, and we sum up this separately and this separately. Once it is calculated, we can find out the beta 1 value, which is approximately equal to 3.54. Once this is found, the slope, once the beta 1 is found out, we can compute this beta naught. To find beta naught, which is equal to y bar minus beta 1 x bar, we already know the equation y equal to beta naught plus beta 1 x, from which this beta naught could be calculated. From the equation above, we know the average of x, average of y, beta 1 is already computed. Substituting all the values, we are getting beta naught as 23.17. This is the beta naught value. Now, in the place of beta naught, beta 1, we can substitute the respective values. So, y cap becomes 23.17 plus 3.54x. This is what we call it as a regression equation. Using this regression equation, now we will be able to predict the salary if the experience is given. For example, if a person is having say 10 years of experience, if we want to compute the salary, we can substitute the value of 10 in the place of x. So the equation becomes y cap equal to 23.17 plus 3.54 into 10. So the value is approximately 58.57. So I can say the person with 10 years of experience will have a salary of, say, $58,570 approximately. This is the predicted salary. Now this equation also gives us some information, that is, for every 1 year of experience, the salary is expected to increase by $3,540. $3,540. Robust regression. This regression analysis is helping us to model the relationships between the dependent and independent variables. In the traditional linear regression, our aim was to fit a model that minimizes the sum of squared differences between the observed and the predicted values. But the linear regression can be highly sensitive to the outliers. In this case, you can see there are some outliers here. Yes, the traditional linear regression will be sensitive to these outliers, and it leads to some unreliable results as well. If the outlier is having a 10-unit error from the existing line, then it becomes 100 units of error to avoid the tilting of line. In this case, we can use Huber laws. The Huber laws function is describing the error, and the estimation procedure f is given here. Here the variable a is referring to the residual, that is, the difference between the observed and the predicted values. We maintain a threshold here as delta. Now we are computing this modulo a, which is the difference between the observed and the predicted value. If this a is less than or equal to this threshold, the loss is computed as half into a square. In case the modulo a is greater than the threshold, we will be using this equation to compute the loss. Threshold value into modulo a minus half into the threshold. Now we have seen the equation for the Huber laws. Now let us find how to solve a problem using it. Consider this data set where hours studied and test scores x and y are given. This is the equation using which you can compute the Huber laws. Upon observing the given data set, we can find 6,20 is an outlier. Let us assume 6,20 as an outlier and the threshold as 1.5. We are going to consider the initial values of W0 as 0, W1 as 1. For this data set, using this Huber laws function, with all these assumptions, we are going to check the value of the Huber laws for the first data point x1 and y2. Let us take this data point, do the prediction y cap equal to w0 plus w1x. So w0 is 0, w1 into x, 1 into 1. Prediction y cap is 1. Now the residual a is equal to the difference between y cap and y, the prediction and the actual value. So when we find the difference between the prediction and the actual value, the prediction is 1, actual value is 2. When we find the difference, we get a value, say 1. Now, using the Huber laws, let us check which equation to be applied. For example, here we are checking the value of mod A. If mod A is less than or equal to the threshold, we will use this equation. Otherwise, we will go for this equation. Here the threshold they have given us 1.5. When we compare A with this threshold, 1 with this 1.5, yes, 1 is less than or equal to 1.5. So the first equation is used, half into 1 square, which is equal to 0.5. Have this value. Likewise, we'll have to proceed for the next data point. The next data point is 2, 4. Now for the next data point, 2, 4, when we are finding the value for 2, 4, in the similar way, find out y cap residual a. In this case, the value of a is greater than the threshold. So this equation is what we have to solve. So the threshold is 1.5. 1.5 into value of a is 2. When we are substituting the values in the equation, the value is 1.875. Huber loss is 1.875. So far we have done for 2 data points. In the same way, we'll have to continue the process for all the data points. We'll have to sum up the Huber losses for all the data points. Later, we'll have to adjust the values of W0, W1 to minimize the total Huber loss. Generally, we will do a lot of iterative optimization methods. After several iterations, we can find out the best fitting parameters. For the example, the best fitting parameters are found to be 0.5 and 1.6 for W0 and W1 respectively. This is the Huber regression line. So once this line is found, we will be able to do the prediction. This is all about the robust regression. In linear regression, the objective is to determine the best fitting hyperplane by minimizing the sum of square differences between the observed and predicted values. When those variables are highly correlated, linear regression will become unstable and it is going to give some unreliable estimates. Ridge regression will address this problem. It's going to introduce a regularization term that will penalize those coefficients, and it stabilizes the model, also reduces the risk of overfitting. Consider the table including years of experience and salary. Here the data looks linear, and the linear regression is used to model the relationship between the years of experience and salary. When we try to fit a line to the data, we will end up in getting a line y cap equal to 23.17 plus 3.54x. When the years of experience is known, we can easily compute the salary. This is reflecting the relationship between the years of experience and salary. When a model is trained using only 2 data points, it will lead to several problems that will result in errors. Because of the limited data, the model is going to create a perfect fit. That is, let us consider some data points here. In case if we are trying to create a perfect fit, that is possible, but that is going to result in overfitting. The reason is when new test data are introduced, in case if these 2 data points are the new test data, the model will struggle a lot and it leads to high error rates. This is going to increase the model's sensitivity, indicating a high variance because of the overfitting, which results in overfitting. Introducing bias in ridge regression is involving a regularization term that's going to penalize the large coefficients. Generally, this is going to avoid overfitting. By accepting this small amount of bias, ridge regression definitely will improve the model's ability to generalize to new data. In ridge regression, the regularization parameter lambda controls the strength of the penalty. The choice of lambda is crucial and we can determine through cross-validation techniques. There are a lot of cross-validation techniques, and these techniques will minimize the error and helps us to achieve a balance between the bias and variance. The first technique, leave one out cross-validation. Here, we are leaving out one sample at a time and the remaining samples are used for training. In the k-fold cross-validation, we will divide the data into k subsets. We will train the model on k minus 1 subsets and evaluates it on the remaining subset. This is going to get repeated for k times. Then stratified cross-validation. Dividing the data into subsets, at the same time we maintain the original class distribution, ensuring they have the same proportion of classes. Suppose if in a data set we have 70% of the data belonging to the label male and 30% of the data belonging to the class female. If this is the case, when we are considering the data, 70% of the data would be taken from the male class and 30% from the female class. This is how the stratified cross-validation is done. Then time series cross-validation. This is evaluating a model's performance on time series data, where we train on the past data and test on the future data. Let us consider this data. Let X represents the feature matrix and Y represents the response vector. The next matrix is X suffix B. In this matrix, we are adding a column of ones to the matrix X. This is enabling the inclusion of an intercept term, and this is ensuring that the regression line will adjust vertically to capture the relationship between the independent and dependent variables. X representing the feature matrix, Y response vector, XB a new matrix which has a column of ones to the matrix X. We can compute W using this ridge regression equation, X transpose into X plus lambda into the identity matrix and the whole inverse into X transpose into Y, where W is representing the vector of coefficients and lambda is the regularization parameter. The first step is, let us choose the regularization parameter lambda as 1. Here, the first factor to be computed is X transpose into X. So for the X matrix, we do compute the transpose. This is X transpose, this is X transpose. We are finding the product of X transpose with the actual X. The first product what we are computing is this X transpose into X, which gives a result 10, 91, 91, 1042. This is the value of X transpose into X. Here, the next step is, after the computation of X transpose X, we have to compute this value X transpose X plus lambda I, where lambda is the regularization parameter and I is the identity matrix. Upon finding the summation of these two, it results in this matrix. Now, the next step is we have to apply the inverse for the same equation, this one. So this is found, and when we are applying the inverse for the same matrix, we are getting a value like this. So this is the final value of it. After which we have to compute X transpose into Y. This is X transpose, this is X transpose, and This is going to be y. When finding out the product of the two, it results in 5546230. In this equation, we are computing x transpose into x plus lambda into the identity matrix, applying the inverse, which results in this matrix, and then calculating x transpose into y results in this matrix. When we find the product of these two matrices, the resultant matrix is 17.5 to 3.97. Once these values are computed, we can substitute this in the prediction equation. So the prediction equation based on the ridge regression is this. Salary is equal to 17.52 plus 3.97 into years of experience. In case if we want to predict the salary for an employee who has 10 years of experience, now we are substituting 10 in the place of years of experience. So the final predicted salary would be 57.22 in thousands. Now this is the equation which can be used to predict the salaries based on any years of experience. Bayesian linear regression is a statistical technique that integrates linear regression with Bayesian inference. It accounts for the uncertainty in model parameters. Also, it is valuable in machine learning for so many reasons because it deals with uncertainty and incorporates prior knowledge. Also, it improves the model. Now, let us see the differences between the linear regression and the Bayesian linear regression. Linear regression is providing point estimates for the model parameters like slope and intercept. Whereas Bayesian linear regression, it provides a full probability distribution for the parameters and predictions, and it helps us in enabling uncertainty quantification and confidence estimation. Linear regression is not easily incorporating the prior beliefs or domain knowledge, whereas Bayesian linear regression, it enables the use of prior knowledge or historical data. Thereby, it leads to more accurate predictions. In linear regression, overfitting can occur. So, some regularization techniques like ridge regression are often used to address this problem. Whereas in Bayesian linear regression, it uses prior distributions to regularize the model. Thereby, it's reducing the overfitting. Bayesian models provide more interpretable results because they are producing distributions over parameters. Linear regression will give a single predicted price and it will not tell how confident the model is. Whereas Bayesian linear regression is providing a distribution of possible prices and it reflects the uncertainty. Linear regression, to predict an outcome y, for example, the income, which is based on the input x, that is the years of experience, the relationship is modeled as y equal to beta naught plus beta 1 x plus epsilon, where beta naught is the intercept, beta 1 is the slope, and epsilon is the error term. In Bayesian approach, it helps us in finding a distribution of possible parameters, which starts with the prior belief about the parameters and updating the belief using the data to get a posterior distribution. Model specification. Let us assume a linear relationship between the input x and the output y, where this beta naught is the intercept, beta 1 is the slope, and epsilon is the error term. Prior distribution. Now assigning the prior distributions to the model parameters beta naught and beta 1, and these represent the initial beliefs about the parameters. that is beta naught and beta 1 are represented in this way, where mu naught, mu 1 are the means and sigma naught squared, sigma 1 square are representing the variances of the pairs. Likelihood. The likelihood function is representing the probability of observing the data given the parameters. Now, assuming the normal distributed errors, yi is represented like this: beta naught plus beta 1 xi comma sigma square. And this is the likelihood of observing yi given xi and the parameters beta naught and beta 1. Posterior distribution. Using Bayes' theorem, now combining the prior and likelihood, we can obtain the posterior distribution of the parameters. That is, probability of beta naught comma beta 1 given the data is approximately equivalent to probability of the data given beta naught comma beta 1, which is multiplied by the probability of beta naught and probability of beta 1. Here, this probability of beta naught and probability of beta 1 are the priors, and the likelihood is represented as probability of data given beta naught comma beta 1, and the posterior is represented as probability of beta naught comma beta 1 given the data. This is the formula which is providing the updated beliefs about the parameters after considering the observed data. Prediction. To predict the output y for a new input x, we can use the posterior distribution of the parameters. Y is represented in this way: beta naught cap plus beta 1 cap into x comma sigma square, where this beta naught, beta 1 cap are representing the posterior means, and sigma square is including both the uncertainty in the parameters and the noise in the data. This approach is allowing the incorporation of prior knowledge and the estimation of uncertainty in the model parameters and the predictions. Logistic regression is a fundamental algorithm in machine learning which is used for binary classification tasks. Unlike linear regression, which could predict continuous values, this logistic regression will predict the probability that a given input belongs to a particular class. Logistic regression is used for binary classification. We'll have only two possible outcomes: pass or fail, spam or not spam. This is the logit function. Logit of p is equal to log of p divided by 1 minus p, which is equal to w0 plus w1 x1, w2 x2. It goes on till wn xn. In this formula, p is the probability of the event occurring. Log of p by 1 minus p is the log odds of the probability p. W0 is the intercept, and w1, w2 till wn are the coefficients or weights for the input features. x1, x2, xn are the input features. The odds of an event is the ratio between the probability of the event happening to the probability of the event not happening. That is, odds is equal to p divided by 1 minus p. That is why we say this as log of odds, log odds. So this is odds. The next function which we need to be familiar is the inverse logit or sigmoid function. P is equal to 1 divided by 1 plus e to the power minus, and the whole expression comes in. Intercept plus W1x1, W2x2, it goes on. The sigmoid function or the inverse logit function, this is playing an important role in logistic regression. What it does is, it converts the linear combination of input features, which we say it as logit, into a probability that is ranging between 0 and 1. So, we will be able to predict whether an outcome belongs to one of the two classes. Let us see an example now. We are going to predict whether the customer will purchase a product based on the age and income. So age and income are the features here. The intercept, age, income, weights, coefficients are given. Let us assume the age is 20 years and the income is $20,000. The first step is we need to find the logit function, logit of P, applying the intercept and weight 1, feature 1, weight 2, feature 2. The value we are getting is 199. When this is applied to P, when we are calculating the sigmoid function, the value is approximately 1, which means this model is predicting a very high probability of the purchase, which is close to 1. Let us see one more example. Considering the intercepts, age, income coefficients, let us assume the age is 16 years, income is $100. Substituting these values in the logit of P, we get the value as minus 0.2. Once that is substituted in the sigmoid function, 1 divided by 1 plus e to the power of minus W0 plus W1x1 plus W2x2, the value would be 0.45. So the thing is, this young customer who has low income, the probability is he is unlikely to make the purchase because the probability is less than 50%. So if the probability is more than 50%, the customer is likely to purchase. Otherwise, he is unlikely to make the purchase. Bayesian logistic regression. Prior. The prior will represent the initial beliefs about a parameter before seeing any data. It's a probability distribution that reflects what is known about the parameter based on the previous knowledge and experience. In Bayesian logistic regression, in case if we want to predict whether a person will buy a product based on their age, and initially it is believed that age is going to have a small positive influence on the likelihood of buying. The prior distribution reflects the initial beliefs about the parameters before seeing the data. A common choice is a multivariate normal distribution, which is represented as P of W, and this is the distribution where M naught is representing the mean vector and S naught is representing the covariance matrix. Likelihood. The likelihood represents the probability of observing the data given a set of parameters. It tells how likely the observed data is. The likelihood for a single observation is P of Tn given W, which is equal to Yn to the power Tn dot 1 minus Yn to the power 1 minus Tn. Here Yn is the predicted probability for the nth data point and Tn is the actual outcome, 0 or 1. Posterior distribution. Using Bayes' theorem, we are combining the prior and the likelihood to obtain the posterior distribution of the parameters. Here the probability of W given T is approximately equivalent to probability of W into probability of T given W. Here we are taking the log of the posterior distribution to make the computations easier. And this is the formula which provides the updated beliefs about the parameters after the consideration of the observed data. Approximate the posterior. MAP estimate, the maximum a posteriori estimate is found by maximizing the posterior distribution. That is the mode of the posterior. Covariance matrix of the posterior. In order to approximate the posterior distribution as a Gaussian, we need to compute the covariance matrix. This is the formula. Sn is equal to S naught inverse plus summation of yn into 1 minus yn pi n transpose, where n ranges from 1 to n. Gaussian approximation to the posterior. The posterior distribution is then approximated as a multivariate Gaussian Q of W, in which this WMAP is representing the mean and Sn is representing the covariance matrix.
Kernel functions provide a powerful tool for enhancing the capability of machine learning algorithms to handle the complex and non-linear patterns available in the data. We can define the kernel function as a real valued function of two arguments represented as k of x, x dash belongs to R. This function is symmetric and non-negative. Symmetric means k of x, x dash is equal to k of x dash, x, and the k of x, x dash value will always be greater than or equal to 0. Now let us see different types of kernel functions. First one is linear kernel. Let pi of x is equal to x. Pi is the transformation function applied on the input feature x. We get the linear kernel defined by just the dot product between the two object vectors, which is represented as k of x, x dash is equal to x transpose into x dash. This linear kernel is useful if the original data is already in high dimension and if the original features are individually informative. In this case, the decision boundary will be already clearly separable as a linear combination of the original features. So it is not necessary for this kernel to work in some other higher dimensional feature space. So when number of features are high, we can go for the linear kernel. Next, let us see about Merkle kernel. Let x is equal to x1 to xn be a finite set of n samples from input space x. The gram matrix of x is defined as k is equal to k of x1, x1 up to k of x1, xn, and here last row will be k of xn, x1 up to k of xn, xn. So this is the gram matrix. If for all x belongs to the input space x, the matrix K is positive definite, then the K is called the Merkle kernel or a positive definite kernel. We can express this Merkle kernel using Merkle's theorem. If the gram matrix is positive definite, we can compute an eigenvector decomposition of it as shown in this equation, that is K is equal to U transpose into diagonal symbol U. So this symbol indicates the diagonal matrix of eigenvalues where lambda is greater than 0. Now if we consider an individual element of K, we can represent it as Kij is equal to diagonal matrix of Ui transpose into diagonal matrix of Uj. Here Ui represents the ith column of the eigenvector matrix U. Similarly Uj represents the jth column. We can define the feature mapping pi of xi corresponding to the input vector xi as pi of xi is equal to diagonal matrix of ui. So based on this, we can rewrite this equation as k of x, x dash is equal to pi of x transpose into pi of x dash, because pi of x can be written as diagonal matrix into ui as mentioned here. So this is the modified equation for Merkle kernel. Next, we have polynomial kernel. The polynomial kernel is used to compute the similarity between two vectors in a feature space over polynomials of the original variables. The formula for this kernel is k of x comma x dash is equal to gamma into x transpose x dash plus r whole power m. Here x and x dash are two vectors in the input space for which we want to compute the similarity. X transpose into x dash is the dot product of vectors x and x dash. This computes the similarity of x and x dash in terms of the directions and magnitudes. Gamma is the scaling parameter which is often called the coefficients. This adjusts the influence of the dot product and controls the width of the polynomial feature space. And r is a constant which is greater than 0. This ensures that the kernel always have a positive value. And m is the degree of the polynomial. Higher the values of m, it leads to more complex decision boundary in the transformed feature space. So if the number of features are less, we can go for the polynomial kernel. Now let us see about sigmoid kernel. The sigmoid kernel is derived from the neural network activation function known as the sigmoid or hyperbolic tangent function. The formula for this kernel is k of x comma x dash is equal to tan h of gamma into x transpose x dash plus r. So the equation is similar to polynomial kernel. Only difference is we are applying tangent function here instead of polynomial. The tan h of x is the hyperbolic tangent function which maps any real valued number to the range minus 1 comma 1. It is often used as an activation function in the neural networks. X comma x dash are the input vectors for which the kernel computes the similarity, and x transpose into x dash is the dot product of vectors x and x dash. Gamma is the scaling parameter that controls the sharpness or slope of the hyperbolic tangent function, and r is the bias term that adjusts the threshold of the sigmoid function. Next kernel is RBF kernel. RBF stands for radial basis function. The RBF kernel function for 2 points x1 and x2 computes the similarity or how close they are to each other. This kernel can be mathematically represented as k of x1 comma x2 is equal to exponentiation of minus norm of x1 minus x2 whole square divided by 2 sigma square. Let d12 be the distance between the 2 points x1 and x2 represented here. We can now represent the d12 as follows. So d12 is the distance between x1 and x2. So it can be represented as x1 minus x2 whole square. So based on this, we can rewrite this equation as k of x1 comma x2 is equal to exponentiation of minus d12 divided by 2 sigma square. The maximum value that the RBF kernel can take is 1 and occurs when d12 is 0, which is when the points are same. That means x1 is equal to x2. When the points are same, there is no distance between them and therefore they are extremely considered similar. When the points are separated by a larger distance, then the kernel value will be less than 1 and almost close to 0, which would mean that the points are dissimilar. So distance can be thought of as an equivalent to dissimilarity measure because we can see that when distance between the points increases, they are less similar and also the kernel value decreases as shown in this diagram. So here we have 3 points. This is x1, this is x2 and this is x3. d12 is the distance between x1 and x2. d13 is the distance between x1 and x3. So the distance of d12 is less than d13 as mentioned here. So if the distance is less, then there will be high similarity and the kernel value will also be high. But if the distance is large, the less similarity will be there and the kernel value will be low. So k of x1 comma x2 will be greater than k of x1 comma x3. Now let us see about illustration of RBF kernel with an example. It is important to find the right value of sigma to decide which point should be considered similar, and this can be demonstrated on a case by case basis as shown here. So first we will consider sigma value as 1. So when sigma is equal to 1, the sigma square also becomes 1 and the RBF kernel's equation can be represented as k of x1 comma x2 is equal to exponentiation of minus of norm of x1 minus x2 whole square divided by 2 sigma square. So since sigma square is 1 here, 2 into 1 is 2. So it is represented like 2. Now the curve for this equation is given here. We can notice that as the distance increases, the RBF kernel exponentially decreases and is 0 for the distances which is greater than 4 as mentioned here. So the region of dissimilarity is happening after the point 4. So in this we have region of similarity. Here also we have region of dissimilarity. So we can notice that when the distance d12 is equal to 0, that is here, the similarity is 1. And as the d12 increases beyond 4, the units of similarity becomes 0. So from this we can see that if the distance is below 4, there will be high similarity. But if it is greater than 4, then the points are less similar. So as we have seen in the previous slide, as the distance increases, there will be dissimilarity. Next, let us assume that sigma is equal to 0.1. When sigma is equal to 0.1, sigma square becomes 0.01 and the RBF kernel mathematical equation is expressed as shown here. In the denominator, we have 2 into sigma square, that is 2 into 0.01 is 0.02. So the curve for this equation is given here. So the width of the region of the similarity is minimal for sigma is equal to 0.1 as shown here, and hence if only points are extremely close, they are considered as similar. So in this curve, we can see the extreme peak and also 0 for the distances which is greater than 0.2. So the points are considered similar only if it is less than or equal to 0.2 as mentioned here. So when the distance increases, there will be high dissimilarity in the regions. Next, let us consider the value of sigma as 10. So when sigma is equal to 10, sigma square becomes 100 and the kernel equation is represented as shown here. In the denominator, we have 200, that is 2 into sigma square, 2 into 100 is 200. The curve for this equation is given here. So the width of the region of the similarity as mentioned here is large for sigma is equal to 10, because of which the points that are farther away also considered to be similar. So the width of the curve is very large for sigma equal to 10 and the points are considered similar for distances up to 10 units as mentioned in this diagram, and beyond the 10 units we can observe the region of dissimilarity. So thus from the above cases it is evident that the width of the region of similarity changes as the sigma value changes. So therefore we have to find the right sigma value for a given data set. So to obtain the optimal curve. Next, let us see about string kernels. String kernels are used when we are interested in matching substrings or sequences within the strings. Let A denote an alphabet, for example A to Z, and A star represent all possible substrings formed from A up to a certain length m. The function pi of x will map a string x to a vector of length A star, where each element j is the number of times a particular substring aj star appears in x. For example, if we have the alphabet A, B and if we consider the substrings of length up to 2, the possible substrings which we can frame are A, B, AA, AB, BA and BB. So the string kernel measures the similarity between two strings, that is x and x dash. So it can be expressed as k of x comma x dash is equal to summation of pi s of x into pi s of x dash. Here pi s of x denotes the number of occurrences of the substring s in x. So the kernel computes the weighted count of the common substrings in both strings x and x dash. Next, let us see about Maton kernel. This is used in Gaussian processes for controlling the smoothness of the modeled function, particularly in spatial statistics and nonlinear regression, which is expressed as k of r as shown here. Here r is equal to x minus x dash, that measures the similarity between x and x dash. V is the smoothness parameter which is greater than 0, and L is the length scale parameter that is also greater than 0, and kv is the modified Bessel function, and this parameter is called as gamma parameter, and when v tends to infinity, this Maton kernel will be reduced to RBF kernel. Lastly, we have Fisher kernel. This is used to measure the similarity between data points based on a probabilistic model such as generative model. The Fisher kernel is defined as shown here. So k of x comma x dash is equal to u of x transpose into I inverse into u of x dash. Here u of x can be expressed like this. So this is called as Fisher score, which represents the gradient of the log likelihood with respect to the model parameters theta. And I is the Fisher information matrix, which measures the expected information provided by the data about the parameters. SVM algorithms use a set of mathematical functions that are defined as the kernel. The function of the kernel is to take the data as input and transform it into the required form. Firstly, a kernel takes the data from its original space and implicitly maps it to a higher dimensional space. This is necessary when dealing with the data that is not linearly separable in its original form. Instead of performing computationally expensive high-dimensional calculations, the kernel function calculates the relationships or similarities between the pairs of data points as if they were in the higher dimensional space. So this diagram indicates that by using the kernel function, we can transform the non-linear separable data into linearly separable data in the higher dimensional space. Now let us understand the purpose of kernel trick. Kernel trick allows us to operate in the original feature space without computing the coordinates of the data in a higher dimensional space. For example, consider x equal to x1, x2, x3 and y is equal to y1, y2, y3. Here x and y are two data points in 3 dimensions. Let us assume that we need to map x and y to 9-dimensional space. We need to do the following calculations to get the final result, which is just a scalar. The computational complexity in this case is order of n square. So we can represent this x in 9-dimensional space as pi of x, which is written as x1 into x1 means x1 square, and we can multiply x1 with x2 and with x3. And in terms of x2, we can write it as x2 into x1, x2 into x2 is x2 square and x2 into x3. And in terms of x3, we can write it as x3 into x1, x3 into x2 and x3 into x3 is x3 square. In the same way, we can represent pi of y. So in short, we can write this as pi of x transpose into pi of y is equal to summation of xi xj into yi yj, where I and j is equal to 1, 2, 3. However, if we use the kernel function, which is denoted as k of x comma y, instead of doing this complicated computations in the 9-dimensional space, we reach the same result within the 3-dimensional space by calculating the dot product of x transpose and y. So, the kernel function is represented as x transpose into y whole square, which can be written as x1 y1 plus x2 y2 plus x3 y3 whole square. This is 3-dimensional space. And in short, we can represent it as xi xj into yi yj. So, where j and I is equal to 1, 2, 3. The computational complexity in this case is order of n. So thus the kernel trick offers a more efficient and less expensive way to transform the data into higher dimensions. Now let us understand the working of kernel function using a numerical example. So we have the feature x here, minus 6, minus 5, minus 4 up to plus 6. So this is represented in 1 dimension and we can represent this x in higher dimension, that is in 2 dimension. So we can calculate x square for each x. So which is represented as for 6 minus 6 it is 36, minus 5 it is 25 and so on. So if we represent this feature x in 1 dimension, we can see the graph here. So we have green points here, that is minus 6, minus 5, minus 4. Followed by it we have red points from minus 3 to plus 3 and then we have 4, 5, 6 at the end. So this data is linearly inseparable. So in 1 dimension it is linearly inseparable. We cannot separate these two classes using a line or a curve. So we can transform this into a higher dimensional space by using the kernel function. So we can square the feature x. So if we square it, we have 36 here. So 6 can be expressed as 36 and then 25, followed by it we have 16, then 9, 4, 2 and 0, and this side we have 1 to 36. So from this diagram we can clearly see that the green points are separated from the red points. So we can easily draw the hyperplane in this higher dimensional space. So thus applying the kernel method to represent the data in 2 dimension is advantageous than in 1 dimension. So thus we have seen about kernel trick in this lecture. SVM is a supervised learning method which stands for support vector machine. And although it can solve both classification and regression problems, it is mainly used for classification problems in machine learning. They are particularly well suited for binary classifications. The purpose of the SVM is to predict the classification of a query sample by relying on the labeled data, which are separated into two groups of classes by using a margin. Specifically, here the data is transformed into a higher dimensions and a support vector classifier is used as a threshold or hyperplane to separate the two classes with minimum error. Before we discuss the concept of SVM in detail, let us understand about dimensions. In simple terms, a dimension of something is a particular aspect of it. Examples of dimensions are width, depth and height. A line on a plane is one dimension as mentioned here. The edges of the square has two dimensions and the cube has three dimensions. Now let us understand about planes and hyperplanes. So plane is nothing but a line which separates the two classes. As mentioned here, we have red points and blue points. So we have a plane here. So if it is one dimension, a hyperplane is called as a point. In two dimensions, it is called as a line. In three dimensions, it is called as a plane. And in more dimensions, we call it a hyperplane. Now let us see the terminologies used in SVM. This diagram shows the terminologies support vectors, hyperplane and margin. Hyperplane is nothing but the line that segregates these two classes that is mentioned in green and red. Now let us see about what are support vectors. The points closest to the hyperplane are called as support vector points. So near to the hyperplane, in the red class we have this point and in green class we have this point. So these points are called as support vectors. And the distance of the vectors from the hyperplane are called the margins. That is the distance of the support vector from the hyperplane is called as margin. So this part is margin and this part is also called as margin. The more farther the SV points from the hyperplane, more is the probability of correctly classifying the points in their respective region or classes. So we should have the support vectors farther from the margins. So SV points are very critical in determining the hyperplane because if the position of the support vectors changes, the position of the hyperplane will also be altered. So thus the support vectors decides the position of the hyperplane. Now let us see the math behind the SVM. Consider a binary classification problem with two classes labeled as +1 and -1. We have a training data set consisting of input feature vectors x and their corresponding class labels y. The equation for the linear hyperplane can be written as y is equal to w transpose into x plus b. Here output y indicates whether it is in a positive class or negative class. W is the matrix which represents the plane's parameters, also the coefficients of x. X is the input data and B represents the intercept of the hyperplane. So in this diagram we can see the hyperplane or decision boundary. So on the decision boundary W transpose into X plus B will be equal to 0. Above the decision boundary it is positive and below the decision boundary it belongs to negative class. So all these red points belong to the negative class and all these green points belong to the positive class. Now let us understand why the output of the equation is either positive or negative in SVM using an example. Consider the problem where the decision boundary passed through the origin as mentioned here. Since it is passing through the origin, the intercept is 0 and the slope is +1. We have single data point on each side of the hyperplane. So this side the red point is -6, 0 and this side we have a blue point that is 5, 2. Let us see whether these points are lying in the positive plane or negative plane by substituting these values into the equation. So our equation is y is equal to w transpose into x plus b. So w transpose is the coefficient which is associated with x. This is nothing but the slope and intercept value. So our slope is +1 and intercept is 0. So we substitute these values into W transpose. So 1, 0 transpose into X value. So considering the red point here we have -6, 0. So we substitute it for X. plus b value is 0, that is intercept is 0. By taking the transpose, we convert it to a column vector. So for multiplication, we have to apply the transpose. So 1 0 into minus 6 comma 0 plus 0, we have the value y is equal to minus 6. So since the sign is negative, this point belongs to the negative class. If we consider this point 5 comma 2, so substituting in place of x 5 comma 2, after taking the transpose and multiplying it and adding it with 0, we get 5. So the sign is positive. So it means that this point belongs to the positive class. So according to this diagram, any point below the hyperplane will always be positive. So below the hyperplane means this. So any point which is lying below the hyperplane will be considered as positive, and any point which is lying above the hyperplane is considered as negative. So this is not applicable for all types of hyperplane. Since the direction is going like this, it is considered as below hyperplane is positive and above hyperplane is negative. But if the direction of line is coming this side, it will be the reverse of this. So thus we have understood why the output of the equation is either positive or negative by using this example. So whenever we choose a hyperplane, we have to choose the plane such that it maximizes the margin between the two classes. So here are the examples of good margin and bad margin. So good margin means there is a large distance between the support vector and the hyperplane. Bad margin means there is only minimal distance between the support vector and the hyperplane. So always we have to choose the hyperplane that maximizes the margin between the classes. To find the optimal decision boundary, the margin has to be maximized in SVM. Let us understand the math behind finding this optimal decision boundary. Consider the positive support vector as point x1 and negative support vector as point x2. The margin would be simply the difference between these x1 and x2. Now let us subtract the equations from one another. That is, for positive class, we have W transpose into x1 plus b is equal to 1. For negative class, we have W transpose into x2 plus b is equal to minus 1. So if we subtract this, we take W transpose as common and we write x1 minus x2. This b plus b, and here we have minus sign, so it becomes minus b. So it gets cancelled, and minus into minus it is plus here. So 1 plus 1 it is 2. Now let us divide. So we need only x1 minus x2. So to cancel this W transpose, let us divide both sides by the length of W, that is the magnitude of that norm of W. So dividing both sides by norm of W, this gets cancelled and we will be having x1 minus x2 is equal to 2 divided by norm of W. Now we have arrived at the equation for the margin. Let us consider this as an optimization function that is need to be maximized using any optimization algorithms like gradient descent. So we are maximizing the equation 2 by norm of W such that yi into wx plus b is greater than or equal to 1. But instead of maximizing, if we minimize, the complexity will be reduced. So to minimize, we have to take the reciprocal of this equation, that is minimize the norm of W divided by 2 such that yi into wx plus b is greater than or equal to 1. So thus this is the equation for finding the optimal decision boundary. Now let us see about what is hard margin. The maximum margin hyperplane or the hard margin hyperplane is the plane that properly separates the data points of different categories without any misclassifications. So we can see in this diagram we have the hyperplane that properly separates the blue points and red points without any misclassifications. So if there is no misclassification, then it is called as hard margin. Now let us see about soft margin. It is also possible that the SVM model can have some percentage of error, meaning we can have misclassification of new data as mentioned here. So we can see that the blue points are along with red points and red points are along with blue points. So this is allowing some misclassifications. So if margin is allowing some misclassifications, then it is called as soft margin. So this has to be integrated into our optimization function which we have derived. So our optimization function is argument min of norm of W divided by 2. So along with this equation, we are adding this classification error, that is C into summation of I equal to 1 to n Ci. So here C indicates the number of error points. In other words, the number of misclassified data points, and this summation is the distance between the marginal hyperplane and the misclassified data points. Now let us see the types of SVM. We have two types of SVM, namely linear SVM and non-linear SVM. Linear SVM uses a linear decision boundary to separate the data points of different classes. So if we are able to separate the two different classes with a straight line or hyperplane, then it is called as a linear SVM. Here we can clearly separate the blue points and red points with this line. But in non-linear SVM, we cannot separate the two categories by using the straight line. So in this case, we can use the kernel functions to handle the non-linearly separable data. So thus in this lecture, we have seen about what is SVM, the math behind the SVM and types of SVM. K-means clustering is a popular unsupervised machine learning algorithm which is used for partitioning a dataset into a predefined number of groups or clusters. The goal of this method is to group similar data points together and discover underlying patterns or structures that are available within the data. The partitioning is to be done in such a way that interpoint distances are small compared to the distances to points outside the cluster. That means we have to minimize the distance between the points which is lying inside the cluster compared to the points which lies outside the cluster. This diagram illustrates the concept of clustering. So before clustering, we have these points all are merged together. We have blue points, red points and green points. After we apply clustering, we can see that all the similar data items are grouped to form a cluster. So here we have three clusters. All red points belongs to cluster 1, green points belongs to cluster 2 and blue points belongs to cluster 3. So this is the idea of clustering. Now let us see the formal definition of K-means clustering. Consider that we have n observations or data points which is denoted as x1 to xn, where each xn is a d-dimensional vector in a Euclidean space. The goal is to partition these n data points into k clusters. We assume that the k is given. Now, the objective is to find a set of cluster centers, also called as centroids, which is represented as mu1 to mu k, such that the data points assigned to each cluster are as close as possible to the cluster center, which thereby minimizes the total within cluster variance. Within cluster variance means we have to minimize the distance between the points which lies inside the cluster. The objective function for K-means clustering is defined as J is equal to double summation of Rnk into Xn minus mu k whole square. Here in the first summation, n indicates the total number of data points. In the second summation, k is the total number of clusters. Xn is the nth data point which is a d-dimensional vector. Mu k is the centroid or center of the kth cluster. And Rnk is the binary indicator variable which takes either value as 0 or 1. So if any data point xn is assigned to a particular cluster k, then Rnk will be 1. If it is not assigned to that particular cluster k, it will be 0. So the goal here is to minimize the objective function. To minimize the objective function, we can use the EM algorithm that alternates between two steps, namely expectation step and maximization step. Here E represents the expectation step and M represents the maximization step. First, let us see about expectation step. Here we minimize the objective function J with respect to the cluster assignments R and K and keeping the cluster centroid mu k as fixed. That is, for each data point xn, we will find the closest cluster centroid mu k and set the value of R and K as 1 for that particular cluster and 0 for the others. This assignment will minimize the square distance that exists between the data point xn and the cluster centroid mu k. This assignment can be formally expressed as Rn k is equal to 1 if k is equal to argmin of xn minus mu j whole square, 0 otherwise. That means if there is only minimum distance between the particular data point and the cluster centroid, then we can assign this particular data point to that particular cluster k, which is represented as 1. Otherwise, it won't be assigned to that cluster and it will become 0. So this step ensures that each data point is assigned to the cluster whose center is the closest, thereby minimizing its contribution to the objective function. Now let us see about the second step in EM algorithm, that is the maximization step or M step. Here we minimize the objective function j with respect to the cluster center mu k and keeping the cluster assignments r and k as fixed. Let us consider the objective function j of the k-means clustering and apply the partial derivative for this equation with respect to mu k, which can be expressed as shown here. Here, since only the terms involving the cluster centroid mu k is contributing to the derivative, we can remove the summation k is equal to 1 to k because it represents entire clusters. So this equation can be written as dou by dou mu k of summation of n equal to 1 to n Rn k into xn minus mu k whole square. By expanding this distance term, we can write it as xn minus mu k transpose into xn minus mu k. By multiplying these two terms, we can write it as xn transpose xn minus 2xn transpose into mu k plus mu k transpose into mu k. Now let us take the derivative for this equation with respect to mu k. We can write it as minus 2xn plus 2 mu k. Since we don't have mu k term here, this will go off. And here if we apply the derivative with respect to mu k, this mu k will become 1. So it is 2 minus 2xn, and mu k transpose mu k is nothing but mu k square. So if you apply derivative for mu k square, it will become 2 mu k. Now by taking the minus 2 outside, we can write it as minus 2 into xn minus mu k. So the derivative of the objective function j with respect to the cluster center mu k can be written as dou j by dou mu k is equal to minus 2 into summation of n equal to 1 to n r n k into xn minus mu k. To find the minimum, we can set this derivative to 0 as mentioned here. Further, we can simplify this equation by dividing both sides by minus 2. So this can be written as summation of n equal to 1 to n r n k into xn minus mu k is equal to 0. Further, we can multiply these terms and we can express it as summation of n equal to 1 to n Rn k into xn. We can take this Rn k into mu k right side. So it becomes is equal to n equal to 1 to n Rn k into mu k. Since mu k is constant for all the terms in this sum, we can take this mu k before the summation. So let us write this term in the left side. So mu k into summation of n equal to 1 to n Rn k is equal to summation of n equal to 1 to n Rn k into xn. Now let us solve for mu k. So this can be written as mu k is equal to summation of n equal to 1 to n Rn k into xn divided by, we can take this to denominator, that is n equal to 1 to n Rn k. So this is the equation for the new cluster centroid. So thus we update the cluster centroid in the maximization step. The numerator here is the sum of all data points xn that are currently assigned to the cluster k. Denominator is the count of the number of the data points assigned to the cluster k. And the equation minimizes the sum of squared distances from the points to the centroid, thereby reducing the objective function j. Now let us see about the working of EM algorithm for k-means clustering. In this figure, we have the plots from A to I. So in the plot A, the green points denotes the data set in a two-dimensional Euclidean space. The initial choices for cluster centers mu1 and mu2 are shown by the red and blue crosses as shown in this diagram. In the plot B, we perform the initial expectation step or E step. Here, each data point is assigned to either the red cluster or to the blue cluster according to which cluster center it is nearer. So if the data point is nearer to the cluster center red, then it is assigned to the red cluster. If it is nearer to the cluster center blue, it is assigned to the blue cluster. So after this E step in plot C, we perform the maximization step. Here the cluster center is recomputed to be the mean of the points assigned to the corresponding cluster. So after updating this cluster center, subsequently we perform the E step and M step alternatively from the plot D to I until the convergence. So in the ith step we can see the convergence where all the blue points are more or less assigned to the blue cluster and red points assigned to the red cluster. This figure presents the plot of the cost function j given by our previous illustration, which is essentially a measure of total distance that exists between the data points and their respective cluster centers. This plot shows the cost function's value after each E step and M step. Here E step is represented using blue points and M step is represented using red points. This is expressed as the algorithm progresses. The green line connecting these points illustrates the rapid decrease in the cost function, which indicates that the algorithm is effectively clustering the data. And the plot also shows that after some few iterations, the cost function j levels off as shown here. It means that the algorithm has been converged. A Gaussian mixture model is a soft clustering technique used in unsupervised learning to determine the probability that a given data point belongs to a particular cluster. Here, instead of assuming that the data is coming from a single Gaussian distribution, we assume that it is generated by a mixture of k Gaussian distributions, each with its own mean and covariance. This model tries to find the parameters, namely mean, covariance and mixing coefficients of these Gaussian distributions that best explains the observed data. This diagram illustrates the concept of Gaussian mixture models. Here we can see that there are three Gaussian functions, that is brown, green and blue, hence k is equal to 3, and each Gaussian explains the data contained in each of the three clusters available, that is cluster 1, cluster 2 and cluster 3. Here we can also see that each Gaussian component is having its own mean and covariance, which is expressed as mu1 sigma 1, mu2 sigma 2 and mu3 sigma 3 respectively. So we can say that all the data points which is belonging to the cluster 1 can come under this Gaussian component, and cluster 2 can come under this Gaussian component, and cluster 3 can come under this particular Gaussian component. But the data points which is lying in this range, it can either belong to cluster 1 or cluster 2, because both cluster 1's Gaussian component and cluster 2's Gaussian components are overlapping here. In the same way, here in this range we can say that it can either belong to this cluster 2 or cluster 3. So from this diagram we can understand that the data is not coming from a single Gaussian distribution, but it is generated by mixture of the k Gaussian distributions. Now let us see the formal representation of Gaussian mixture distribution, which can be written as P of x is equal to summation of k is equal to 1 to k pi k into normal distribution of x given mu k comma sigma k. Here P of x is the overall probability density function for a data point x. In the right side, the expression is the weighted sum of k Gaussian components. So here summation of k is equal to 1 to k means it represents k Gaussian components. And pi k is the mixing coefficient for the kth Gaussian. It indicates the probability of a data point belonging to the kth cluster whose sum of all values will be equal to 1 as mentioned here. That is summation of k is equal to 1 to k, pi k is equal to 1. That means the value of pi k will be ranging from 0 to 1. This function also indicates how big or small the Gaussian function will be. And this normal distribution is the probability density function of a Gaussian distribution, which is having the mean mu k and covariance matrix sigma k. In the context of GMM, we know that each data point x is assumed to be generated by one of the k Gaussian distributions. So, to know what is the probability that a data point xn is coming from the Gaussian component k, we can express it as P of zn k is equal to 1 given xn. That means given the data point xn, what is the probability that it is belonging to the kth Gaussian component, which is expressed as zn k is equal to 1. Here z is the latent variable which takes only two possible values. It is 1 when x is coming from the particular Gaussian component. Otherwise it will become 0. We can also state this as pi k is equal to p of zk is equal to 1, which means that the overall probability of observing a point that comes from the Gaussian k, that is the right hand side, is actually equivalent to the mixing coefficient which is left hand side for that particular Gaussian. This makes sense because pi k indicates how bigger or smaller the Gaussian is. So the bigger the Gaussian is, the higher we would expect this probability to be. Now let z be the set of all possible latent variables which can be expressed as z is equal to z1 to zk. We know that each z occurs independently of others and they can only take the value of 1 when k is equal to the cluster the point comes from. Therefore, we can express this z as p of z is equal to p of z1 is equal to 1 whole power z1 into p of z2 is equal to 1 whole power z2 up to p of zk is equal to 1 whole power zk, which can be expressed in short as product of k is equal to 1 to k pi k whole power zk. So whenever the exponent zk is 1, then it indicates that the particular data point is having the high probability that it belongs to a particular Gaussian k. To find the probability of observing our data, given that it came from the Gaussian k, following the same logic we used to define p of z, we can state p of xn given z, that is given the Gaussian component k, what is the probability that xn belongs to that particular Gaussian k. So this can be written as product of k is equal to 1 to k normal distribution of xn given mu k comma sigma k whole power zk. But our initial aim is to determine the probability of z given our observation x, not xn given z. So from the product rule of probabilities, we can write p of xn comma z as p of xn given z into p of z. So this is what we have derived now, that is p of z and p of xn given z. But we need to find p of xn, not p of xn comma z. So we have to get rid of this particular z. So to get rid of this z, we can marginalize this equation. Marginalizing means we have to either perform integration or summation. So if it is discrete data, we have to perform the summation. So here z is discrete value. So let us apply summation. So we can write p of xn is equal to summation of k is equal to 1 to k p of xn given z into p of z, which in turn can be written as summation of k is equal to 1 to k. So for p of z we can substitute pi k and p of xn given z can be expressed as normal distribution of xn given mu k comma sigma k. So to find the probability of z given x, we can use the Bayes rule. Bayes rule can be formally expressed as p of a given b is equal to p of b given a into p of a divided by p of b, where the denominator p of b is the marginal probability. Here we assume that zk is equal to 1 as a and xn as b. So we can express it as p of xn given zk is equal to 1 into p of zk is equal to 1 divided by p of xn, which can be expressed like this as shown in our previous slide. So from our earlier derivations, we know that p of zk is equal to 1 can be expressed as pi k, p of xn given zk is equal to 1 can be expressed as the normal distribution, and p of xn can be expressed as the marginal distribution, that is summation of k is equal to 1 to k pi k into normal distribution of xn given mu k comma sigma k. So now let us replace this with this equation. So we get from this the gamma of z and k. Here we view the pi k as the prior probability of zk is equal to 1, because initially we don't know the values for z, so we assume it. So it is called as prior probability, and once the data is being observed, then we can find the posterior probability, that is gamma of z and k. So gamma of z and k is the corresponding posterior probability which we determine once we observe the data x. This gamma of z and k can also be viewed as the responsibility that the component k takes for explaining the observation x. Now let us understand the concept of Gaussian mixture models using these plots. So we have three plots A, B and C. In the plot A, we have the joint distribution P of Z into P of X given Z. This is called as the prior probability, where the three states of Z corresponds to three components of the mixture. The samples are represented in three colors, namely red, green and blue. Each color represents one state of Z, and this data set is referred to as complete because we are assuming the values of Z and it is known. Next, in the plot B, we have the marginal distribution P of X. Here we are ignoring the values of Z and just plotting the X values. So all the values are shown in magenta without distinguishing between the different components of the picture. This data set is called as incomplete data because the values of Z are not known here. Next, in the plot C, it is called the posterior probability. This shows the samples, but the colors represents the responsibilities gamma of Z and K associated with each data point Xn. This is achieved by plotting each point using a mix of red, green and blue colors, where the proportion corresponds to the responsibilities gamma of Z and K for K is equal to 1 to 3 respectively. Here, these colors visually indicate the degree of association of each point with each of the three mixture components. So all these components are belonging to red cluster and these points belong to green cluster and this one belongs to blue cluster. But in the overlapping regions, we can see that it is a mix of red and green. So it can have either the probability of belonging to red or green. In the same way here it belongs to either blue or green. So it is the mix of blue and green color. First, let us understand the likelihood function for GMMs. We know that a Gaussian mixture model is a probabilistic model that assumes that the data points are generated from a mixture of several Gaussian distributions instead of a single distribution, and each will have its own mean and variance. The goal of MLE in the context of GMMs is to find the parameters of the model, namely the means mu k, covariances sigma k and mixing coefficients pi k for each Gaussian component that will maximize the likelihood of the observed data X. We can define the likelihood function for a GMM as P of X given mu sigma pi is equal to product of n equal to 1 to n into summation of k is equal to 1 to k pi k into normal distribution of xn given mu k sigma k. For maximization, let us apply the log likelihood for this function. So after this we get this equation. Here this product becomes summation after applying the log. So remaining and all same. A key issue in MLE for GMMs is singularities, which is represented in this diagram. This problem arises when a Gaussian component's mean mu k approaches exactly one of the data points xn as shown in the right hand side of this diagram. We can see that this mean is approaching to exactly one data point, and because of this its variance will become very small. In this case, the likelihood function can become extremely large because the Gaussian density tends to infinity as the variance is decreasing. As the variance of one Gaussian component approaches to 0, the log likelihood can go to infinity, which in turn leads to a non-optimal solution and it is not meaningful for the practical applications. So, to address the problem of singularities in MLE for GMMs, the expectation maximization algorithm is used. This method alternates between two steps, namely expectation step and maximization step. Here, expectation step is nothing but E step, which estimates the expected value for the latent variables given the current parameters. And in M step, we maximize the likelihood function with respect to the parameters using the expected values computed in the E step. These steps are repeated iteratively until the convergence, that is until the parameters stabilize or change very little between the iterations. Now let us see the steps in EM algorithm. First step is initialization. Here we start with initial guesses for the parameters, namely mean, covariance and mixing coefficient for each Gaussian component k is equal to 1 to k. This can be done randomly, or we can use some heuristic algorithm like k-means clustering. So we are making the initial guess about the parameters in the initialization step. The second step is E-step or expectation step. In the initialization step, we have assumed the values for parameters. So based on the current parameter values, in this step, we compute the posterior probabilities that each component k was responsible for generating each data point xn. This is also known as responsibilities, which can be expressed as gamma of z and k. This is calculated using the Bayes rule, which we have seen in our previous lecture. So gamma of z and k can be expressed as pi k into normal distribution of xn given mu k comma sigma k divided by summation of j is equal to 1 to k pi j into normal distribution of xn given mu j comma sigma j. Now in the third step, that is in the M step, we update the parameters mu k, sigma k and pi k to maximize the expected log likelihood using the responsibilities that we have computed in the E step. The complete log likelihood of the data xn given the latent variables zn and the parameters mu k, sigma k and pi k can be expressed as shown here. Here we take the log for pi k and the normal distribution. In this case, the term z and k can be replaced with the responsibility component gamma of z and k, which is computed in the E step. So, the expected log likelihood with respect to the responsibilities gamma of z and k can be expressed as shown here. So, we can see that z and k is replaced with gamma of z and k. Now, we have the complete log likelihood function. Let us update the parameters mu k, sigma k and pi k here. So, first let us update the mixing coefficient pi k. The log likelihood term involving pi k in this equation is taken separately, that is q of pi k is equal to double summation of gamma of z and k into log pi k. So to maximize this q of pi k with respect to pi k, subject to the constraint which we know summation of k is equal to 1 to k, pi k is equal to 1, we use the Lagrange multiplier method. Because whenever we have a constraint on one particular equation, if we want to maximize or minimize that equation, we can use the Lagrange multiplier method. So by applying the Lagrange multiplier method, this equation becomes as shown here. So here we have this term plus lambda into summation of k is equal to 1 to k pi k minus 1. So this is the Lagrange multiplier method. To find the optimal values of pi k, we need to take the partial derivative for the Lagrangian equation which we have derived. So in this case, let us consider the first term. So if we apply the derivative with respect to pi k for this first term, this log pi k will become 1 by pi k. So it can be expressed as summation of n equal to 1 to n gamma of z and k divided by pi k. Now let us consider the second term. If we differentiate with respect to pi k, this pi k will become 1 and this constant will become 0. So we will be having only lambda as expressed here. Now let us combine these two terms and set the derivative to 0 as shown here. To solve for pi k, let us take this lambda to the right side. So it becomes minus lambda. And to get pi k, we take this lambda to the denominator. So it becomes minus summation of n equal to 1 to n gamma of z and k divided by lambda. To get the value of lambda, let us use the constraint summation of k is equal to 1 to k, pi k is equal to 1. So in this equation, let us substitute this equation for pi k, so which can be expressed as shown here. So here let us take this lambda outside the summation. So it becomes minus 1 by lambda into double summation of gamma of z and k is equal to 1. So we can express this summation of n equal to 1 to n as n and summation of n equal to 1 to n gamma of z and k as nk. So n is the total number of data points and nk is the effective data points which contribute to the component k. So since we can express nk as n, in this equation we can replace this double summation of gamma of z and k with n. So it can be written as minus n by lambda is equal to 1. So now we can get the lambda value. So lambda is equal to minus n. So if we substitute this lambda value in this equation, we can write pi k as pi k is equal to nk divided by n. So where nk is nothing but this summation of n equal to 1 to n gamma of zk. So in the place of lambda we write the minus n, so it becomes plus. So we have final expression as pi k is equal to nk divided by n. So thus we have updated the mixing coefficient pi k. Next, let us update the parameters mu k and sigma k. The mean mu k of the component k is updated by maximizing q with respect to mu k. This gives the update mu k is equal to summation of n equal to 1 to n gamma of znk into xn divided by summation of n equal to 1 to n gamma of znk. Here, this is the weighted average of the data points where the weights are nothing but the responsibilities gamma of znk. Similarly, we can update the covariance matrix sigma k as shown here. So we replace the xn with xn minus mu k into xn minus mu k transpose. This is the weighted covariance where the weights are the responsibilities gamma of znk. So thus we have updated the mixing coefficients mean and sigma k in the m step. So we iterate between the e step and m step until the convergence of the EM algorithm.
Hierarchical clustering. There are two approaches to hierarchical clustering. One is bottom-up approach, agglomerative clustering. The other one is a top-down approach, that is the divisive clustering. Both the methods are using the dissimilarity matrix as input. Here in the bottom-up approach, the most similar groups are merged at each step. Whereas in the top-down approach, the groups are split using different criteria. In this figure, we could see using the single link clustering, let us see how it is grouped. This is the city block distance. Here pairs 1, 3 and 4, 5. They are both distance 1 apart. So we will be merging 1, 3 first and then 4, 5 next. That is, this is the dendrogram, the visual representation of the merging. You could see 1 and 3 are merged at first and 4 and 5 are merged because they are distance 1 apart, and after which these two clusters are merged, and the next level is this 2 is merged with this particular cluster. Now agglomerative clustering. This agglomerative clustering, it starts with n groups in which initially there will be one object, and at each of the step we are merging the similar groups, two most similar groups. So we will proceed this until there is only one single group. There are actually three types of agglomerative clustering. So depending on how we are defining the dissimilarity between the groups of objects. The first one is single link. Here in single link clustering, we also call it as a nearest neighbor clustering. The distance between any two groups is defined as the distance between the two closest members of each group. That is, here G and H are the two groups. We are going to define the minimal distance between the two closest members of the each group. For example, here AB are the members of this particular cluster and CD are the members of this particular cluster. And a single link clustering, you can merge if B and C are at a minimal distance. You need not consider A and D as far as a single link is concerned. Moving on to complete link. In complete link clustering, it's also called furthest neighbor clustering. The distance between the two groups is defined as the distance between the two most distant pairs. That is, this group G and H, the distance between the two most distant pairs is considered here. So here again, A, D are at the most distant pairs. A and D are the most distant pairs. So which means within the threshold, both A, B should be within the threshold to C and D. Average link. So for average link, we need to measure the average distance between all the pairs. So average of the distance between all the pairs. Here this n suffix g and n suffix n are the number of elements in groups G and H. Divisive clustering. Here in divisive clustering, you start with the data in a single cluster. Then recursively, we are dividing that cluster into two clusters in a top-down fashion. This picture illustrates both agglomerative and divisive clustering. As far as agglomerative clustering, it begins here. The step 0 starts here. So each of the point is treated as a separate cluster. And in step 1, we are merging A and B. Then step 2, we are merging D and E. And in step 3, we are merging C, D, E. And step 4, finally, all the clusters are merged and formed as a single cluster. Whereas in divisive clustering, the step 0 starts from here, which means we start from a single cluster. So it's step down, CDE forms a separate cluster, and then in the successive steps, they are dividing, and finally they end up in single cluster, each and every data point as a single cluster. Bayesian hierarchical clustering. So this approach, this is the algorithm representing the Bayesian hierarchical clustering. Initially, each and every data point will be treated as a separate cluster. So n number of points are there. Each of the data point will be treated as a separate cluster. The next step is we need to compute the probability of that particular cluster given the Ti. T suffix I specifies the prior information. We are repeating these steps 4 to 8 until all the clusters are merged. So for each of the pair I and j, we need to compute the probability of that D for the two pairs I and j given the prior information of that ij. We need to find the pair of those two clusters with the highest merge probability R suffix ij. So find some pair, find the clusters di and dj, and we need to do that with the highest merge probability of it. And the next step is we are merging that di and dj as a single cluster dk. After merging that di and dj as a single cluster dk, we can delete the two clusters di and dj. We need to repeat these steps until all the clusters are merged. Let us see a problem. Now we are going to perform the hierarchical clustering using a single link and complete link on the data set, and the distance matrix is given. We need to derive the resulting cluster structure. This is the distance matrix. We have 4 points and the distance between each pair is given here. Let us consider this distance matrix. For single link, the distance between two clusters is the shortest distance between a pair of elements from the two clusters. When the distance is 0, there will be 4 separate clusters. When the distance is 1, so there are points P1 and P2 within this threshold. So we can merge P1 and P2 as a single cluster. P3, P4 will be acting as a single cluster, separate clusters. When the distance is 2, from the distance matrix, we can understand that P2 and P3 are at a distance 2. So this P3 can also be merged with this cluster as P2 is here. So P1, P2, P3 will be a single cluster and P4 will be separate now. When the distance is 3, looking at the distance matrix, we can find P3 and P4 are at a distance 3. So this P4 can be merged with this group. Now all the points will form a single cluster P1, P2, P3, P4. So when the distance measured is 3, all the 4 clusters are merged into a single cluster. This is happening with a single link. And the corresponding dendrogram is represented here. This dendrogram shows the visual representation of how the merging is happening. So at a distance 1, we are able to merge P1, P2. At a distance 2, we are able to merge P3 with that group. When the distance is 3, we are able to merge P4 with that group. Next, complete link. This is the distance between two clusters, the longest distance between a pair of elements from the two clusters. Now here, when the distance is 0, there are 4 clusters. When the distance is 1, we are able to merge P1 and P2, fine. When the distance is 2, from the distance matrix, we can find only P3 is within the threshold with P2. And looking at the clusters here, as far as a complete link is concerned, both P1, P2 should be within the threshold to P3. Only then both the clusters could be merged. So that will remain as such. We can't merge as of now. So increasing the distance to 3, again looking at the distance matrix, P3, P4 are at a distance 3. P3 and P4 are at a distance 3. So it is possible that we can merge P3 and P4 and make it as a cluster. So when the distance measure is 4, we need to check whether we will be able to merge these two clusters, but that's not possible because when the distance measure is 4, both P1, P2 should be at a distance 4 with these 2 points. So that's complete link. So where looking at the distance matrix, we can find P1 and P4 are at distance 5, not within the threshold. Also, P2, P4 are at a distance 6. That is not within the threshold. So that will remain as such. When we increase the distance 5, again, the clusters will remain as such. We can't merge. So still there are 2 clusters here. When we increase the distance 6, yes, these points P1, P2 are within the threshold level, say distance 6 with these 2 points in a different cluster. So when the distance measure is 6, it's possible to merge these 2 clusters. So finally, using complete link, we can merge all the clusters as a single cluster only at the distance measure of say 6. So this is the difference between a single link and complete link. And this is the dendrogram representing the complete link. So at a distance measure 1, we are able to merge P1 and P2. At a distance measure say 3, we are able to merge P3 and P4. And at a distance measure 6, we are able to merge these 2 clusters. In this video, we have learnt about hierarchical clustering.